This conference will now be recorded.
Well, since I hope everyone is here and will have a lot to cover, we really should begin our today's webinar. I really appreciate you all for attending today's webinar. A very good morning, afternoon, evening to one and all present here virtually with me today. Let me introduce myself. My name is Rachel McLean, Conference Secretary at Coalesce Research Group LLC, and I will be available for any of your queries or questions throughout the webinar to help you technically and organize the webinar successfully. For the next 5 minutes, please allow me to give a brief description about our organization, College Research Group, and also further instructions. College Research Group LLC is very delighted to welcome you all the speakers, supporting associations, students, and delegates to present virtually with us today. With the aim mark the scientific excellence by facilitating conversations, sharing knowledge, College Research Group follows throughout the objective of setting standards and delivering excellency in the research among the researchers, academics, and industries. Proclaim the research throughout conducting events and online webinars from various fields of science, especially from the stream of medicine, science, engineering, and technology. With a short description duration, we have succeeded in creating a platform for developing a strong professional network with the people across the world from their respective fields that they have been connected in a while. As a global scientific event organizer, we plan and carry out international conferences, meetings, seminars, symposiums, and workshops, providing the best delegate experience, excellent networking opportunities, conversations leading to innovations, learning new opportunities, lasting working relationships, and professionalization with the professionals across the global networks. Just recently, we have also started our own platform for open access, pre-reviewed scholarly literatures, where all the content is freely available without any charges to the readers. We aim to share the new recent advances throughout the scientific publications, which will help in minimizing the borders and contributing the use of research works of eminent authors, scientists, researchers, research scholars, students, etc., across broad spectrum of medical, clinical, pharma, and engineering scientific disciplines and its subspecialties to promote the ideas which will guide the development and facilitate the use of scientific information and ensure its quality and also will be connecting link between researchers and scientific community. We are committed in ensuring that our journals are disseminated worldwide so that researchers are available to access our content whenever and wherever they need it. As begin the very new journal, we have coined up some interesting journals and have also formed the editorial boards and will be very glad if any of your today's attendees, speakers, students, or delegates could extend your support by checking the web journal website and will be interested in publishing an inaugural issue at any of these journals according to your area of expertise. We will also send an email with all the details about the journal after the commitment of the webinar. Do take your time to check the website. Finally, I would like to thank the attendees of the participants of today's webinar. Hope you enjoyed the webinar and gain knowledge from the sessions today. We also hope your participation will contribute to new research findings and that will lead to the new collaborations and research initiatives. Before we start with the sessions, I guess some of you will be new to the GoToMeetings app. Let me just explain you the important tools required for the presentation. On the GoToMeetings app or web page, you can find your 4 icons at the bottom center: mic, camera, screen, and or leaf. Mic. Click on the to mute or unmute yourself. I request you all to stay muted while our speakers are presenting the research work so that it does not cause any disturbance to them. Camera button, you can use this button to share or unshare the web camera. If you have the option to share the webcam, you can do it, or it's completely your choice. Screen button, you can use this button to share your screen. This is the main part during your presentation. After I call your name, From my side, I will be making you the presenter, and now and only I give the permission you will be able to share your screen. So once I make you the presenter, you can click on the screen button and you will be find a pop-up window to share your screen. End or leave button. This is your fourth icon where you can use this to leave the session. On the top center, you can use the option to change your display settings. At the top right corner, you will be have three icons: people, chat, and settings. In that chat option, you can chat with me or any other participants. For the settings, you can use this button to check for the settings of your speakers and microphones. As I mentioned, kindly remain muted during the presentation so that the presenters do not get disturbed. And for any questions, you can ask the questions or you can send your questions in the message box too. Well, let's not to take much of your time. Finally, I would like to thank you to request you to please give us a brief introduction about yourself before starting with the session so that we can know about your virtually. And now let's move into our sessions. The first presenter is Dr. Chicha Chichao Ma from Southeast University, China. Doctor, are you ready with your presentation?
Yes, thank you.
Oh, thank you. Now I'm going to make you as a presenter now. Please share your screen.
Okay. Can you see my screen?
Yes, please make
Okay,
it as a full screen. Yep.
okay. Thank you for coming to listen in my presentation. Wait a minute. Thank you for coming to listen in my presentation. My name is Zhichao Ma, and I'm from Southeast University, China. Today, I will introduce the Moses non-twist theorem for nearly integrable mappings with self-intersection property. This presentation is divided into two parts. Firstly, we introduce a Moses non-twist theorem, including background and results. Then, we will apply these results and include this part will including symmetric case and asymmetric case. We first introduce the background of the nearly integrable mappings. Consider the twist mappings M, het theta equals theta plus omega I plus phi theta I, het I equals I plus psi theta I, where theta I belongs to t times interval AB with t equals R modulus 2 pi z. Here z is a set of integrals. The above mapping first appeared in the work of Poincaré about the restrict three-body problem. Lots of mathematicians and physicists were focused on this mapping, and there are many famous works, such as Poincaré's last geometric theorem, also called Poincaré-Birkhoff theorem, as this theorem was proved by Birkhoff. Moses twist theorem and small twist theorem, and so on. In this presentation, we mainly focus on Moses twist theorem. This result was proved by Moses in 1962. Suppose that the mapping M has self-intersection property, which means that any groove gamma R equals lambda theta equals lambda theta times plus 2 pi always intersects its imagined groove M circle gamma. Assume M is a C 333 smooth mapping. Suppose that omega I satisfies the monotone twist condition. In this form, if phi and psi are significantly small, then there exists a contour-like family of invariant closed grooves for the mapping M. Here, we should note that the smoothness condition is too strict. We also should note that these twist conditions can be weakened. Firstly, we said Riemann succeeded in dropping the smoothness condition from C 333 to CP with P is larger than 5. Well, Moser pointed out that resonance proof leads to invariant closed groups even for CP with P is bigger than 3. Similarly to Moser's twist theorem, we have the following small twist theorem. Consider the twist mapping in this form. Here, eta belongs to interval 0, 1 is a small parameter. The existence of eta is the reason called small twist. We also suppose omega I satisfies the monotone condition 1. This condition, we suppose the mapping M is a C4 smooth mapping and has self-intersection property. If phi and psi are significantly small, then the mapping M star possesses a contour-like family of invariant closed groups. Here, the monotone twist condition is also necessary. In fact, this condition is significant but not essential, and it can be weakened to the twist condition in sense of resonance non-degeneracy, which means there exists an integral k is larger than 0 such the following form, or the general twist condition, which means omega interval AB equals interval C1, C2, with C1 not equals C2. In this presentation, we mainly focus on the case that the twist condition is not satisfied, which means omega I always equals to omega 0. Here, omega 0 is a consistent. We say that the mapping is non-twist. Now we consider the following non-twist mapping M imizinal. Hit R equals I plus psi I theta imizinal. Hit theta equals omega 0 plus theta plus phi I theta imizinal, where I theta belongs to interval -1, 1 times t, and imizinal is a small parameter. Below we will give a similar result to Moser's twist theorem about this non-twist mappings. We called this result Moser's non-twist theorem. Before starting our result, we give some notations. For gamma and tau, define the delta gamma tau in this form. Here, this inequality implies that omega is a definite number. Let U delta equals interval 0 delta. Let C mu interval -1, 1 times t U delta be the set of functions which are C mu smooth in I theta on interval -1, 1 times t and continues in parameter imizinal on U delta. For any phi belongs this set, we define the supernorm of phi in this form. Now, we can state our main result in this presentation. It is called Moser's non-twist theorem. Assume that omega 0 belongs to delta gamma tau and phi psi belongs to C mu interval -1, 1 times t U delta, with mu is larger than 4 tau plus 5. Assume that the mapping M has self-intersection property and satisfies this limit condition. Then for hit gamma and hit tau, there exists a significantly small epsilon ring and a significant subset E such that for any epsilon belongs to E, the mapping M admits an invariant closed group with rotation number omega star. Here, omega star goes to omega 0 as epsilon goes to 0. Moreover, omega star is also a definite number. Furthermore, for all delta, the set E has cardinality number of the continuum. For this result, we need to point out some things. Firstly, in the above theorem, the mapping M is continuous in parameter epsilon on U delta. If the mapping is if the mapping M is C1 smooth in imizinal, then for all delta, the set E has a positive Lebesgue measure. Secondly, the smoothest condition in this result is stricter than that in Moser's twist ceremony, because the rotation number omega star belongs to delta hit gamma hit tau requires higher smoothness condition. Now we are going to the second part of this presentation. To be precise, we will use this result to consider the Lagrange stability of some second-order equations. Consider the nonlinear defining equation in this form, where V is a continuous map from R times T to R. We say this equation is Lagrange stability. That means for any solutions of it, xt is well defined for all t belongs to R and satisfies super absolute x plus absolute dot x is more than positive infinity. The first boundedness result of the above equation was given by Morris. By means of Moser's twist ceremony, the author proved the Lagrange stability of this equation. Here, hx equals 2 times circle x. And then this result was generalized to the superlinear situation. That means hx divided by x goes to infinity as absolute x goes to infinity. We mainly concern about the asymptotic situation, which means that the following two limitations exist. The first limitation is x goes to positive infinity, and the second one is x goes to negative infinity. At first, we consider the symmetric case, which means these two limitations are same. Consider the following defining equation in this form. Here, omega belongs to n and phi x is in this form. We should note that phi x goes to L. Phi x equals L when x goes to positive infinity, and phi x equals negative L when x goes to negative infinity. If L is larger than 0 and P satisfies these conditions, by developing a variant of small twist theorem, Ortega proved the Lagrange stability of equation 2 of this equation. Moreover, Liu also proved a more general result under this limit assumption. Clearly, L is larger than 0. This condition is covered by condition 3. In both of two results, the condition 3 is important as it is used to ensure the twist conditions of the corresponding Poincare map. Recall that our Moser's non-twist ceremony does not need any twist condition, so it motivates us to consider the Lagrange stability of equation 2 without condition 3, without these conditions. So we have the first result of the applications. Consider these defining equations and suppose omega is a defining number. Also, we suppose G is a semi-smooth in X and continuous in T. We also suppose G satisfies this condition. Then, this defining equation possesses Lagrange stability. At last, we consider the asymmetric case, which means these two limitations are different. So we consider these differential equations. Here, a and b is larger than 0. X positive equals max x0, x negative equals max negative x0. Here, ax positive minus bx negative is the asymmetric term. This differential equation arises from a mechanical model describes the motion of particles which is subjected to a asymmetric restoring force. If this term not belongs to Q, here Q is the set of rotation number, and PT satisfies these non-zero average conditions. Odega and Wang independently proved that this equation possesses Lagrange stability. Here, these conditions, called non-zero average conditions, is used to ensure the twist conditions. And similarly, by our Moses non-twist ceremony, we want to prove the Lagrange stability of 5 of these conditions without these non-zero average conditions. So we have the second ceremony about the applications. Consider the following differential equations. In this form, suppose omega also is a definite number. Assume g xt belongs to c mu plus 1 r times t, with mu is larger than 4 tau plus 5. Similarly, we also suppose g satisfies this condition. Then this equation possesses Lagrange stability. Compared with this result and this result, we can see that the smallness assumption in equation 7 on G is stricter than that in equation 4. This is the smooth conditions in about equation 4. Here, it requires C mu smooth, and in equation 7, it requires C mu plus 1. This difference is due to that the asymmetric term ax negative minus bx, ax positive minus bx negative affects the smoothness of the corresponding Poincare map. That's all. Thank you very much.
Thank you, Dr. Chichama. Is anyone having any questions? I think there are no questions. Let's move to our next presentation by Dr. Wenxing Yin from Southern University, China. Doctor, are you ready with your presentation?
Okay.
Okay, now I'm going to make you as a presenter now. Please share your screen for the presentation.
Yes.可以了，对吧？摄像头打开了。Hello everyone. I'm Wen Sheng from the School of Mathematics, Southeastern University, China. I'm honored to have the opportunity to participate in international webinar on applied science and engineering. Today, I'm sharing with you one of our recent work. This work was done in cooperation with the Professor Jin De Cao. The topic is path stability of triangular GSD and cooperation and application to the for-order filtering. There are four parts in my report, including introduction, problem formulation, and main results, sketch of the brief, applications, and discussions. First, we introduce the concept of path stability of problem. Given SDE, which is described by the following equation. This is the scholastic different equation. The path stability has been well studied. One can refer to the monograph to Smith, published in 1918, and more, published in 2007. The stability analysis to SD under G expectation formulation began from John published in Applied Mathematical Letter, and the causal exponential stability problem was extended in Lee published in GMI. The G explanation theory proposed by Peng provides a dynamical nonlinear expectation framework. Given a coordinate space, sample space omega, with all omega 0 is equal to 0, denoted by B the coordinate process. Then for bounded Lipschitz function phi, the G expectation for random variable phi is constructed with the following PDE. Then iteratively defined G expectation for Lipschitz omega. Indeed, while we constructively define the expectation of phi for phi belong to Lipschitz omega, we also have given distribution meaning to the canonical process, which are referred to as G promotion. In particular, G promotion has independent increments. For additive, Peng defined the scholastic integral. The totality of all such atoms will be denoted by mg0. mg2 is the completion of mg0 under this number. Therefore, this scholastic integral has got its meaning for eta belong to mg2. Stochastic different equation derived by G promotion has been established. First, we consider a GSDs with an output equation given by equation 1. PS denotes the state vector, QS denotes the output vector, and VS is the control input. BI can be viewed as meaning uncertainty potential, and CI can be viewed as volatility uncertainty potential. The well-positiveness of the solution to equation 1 are guaranteed under Lipschitz continuous and linear growth conditions. For any VS, A1, B1, C1, A2, B2, and C2 are identical to 0, then we get P and Q are identical to 0. It is a trivial solution. Now we introduce the concept of path stability of GSDs. The trivial solution to first equation is quasi-solely exponentially stable if any P0 belong to Rn, then the inequality holds. We state a main lemma. Suppose that there exists 3 constants Ki belong to R and K3 is greater than 0, such that 1, 2, 3. Under the 1, 2, 3, the path solution of the first equation of 1 satisfies this inequality too, especially the solution of the first equation of 1 is quasi-so exponentially stable if the inequality holds. Then we introduce the filtering problem. The for order filter observed is described as follows, where phi is the matrix to design. Let ES be the observation error, then we get the equation 4. Letting YS, F, G, H write this form. We rewrite equations 1 and 4 as equation 5. The GST SD5 belong to the class of the following triangular GSD with the known input of the form equation 6, where Y1 belong to RD1, Y2 belong to RD2 with the initial data. Our aim is to obtain the quasi-so exponential stability to triangular GSD6. We consider the following isolated GSD equation 7. The well-positiveness of system 6 and 7 under Lipschitz continuous and linear growth conditions, C. Lee, published in GMI. For any width F1, F2, G1, G2, and HI are equation 1, then we get Y and Y bar is identical to 0, a trivial solution. The coefficient of equation satisfies the form. We state our main theorem. Under H1 to H3, the GSD6 is quasi-so exponentially stable only if and if the saluted GSD is quasi-so exponentially stable. In other words, there exists two constant eta is greater than half of the E and gamma is greater than 0, such that inequality at there is a constant delta such that inequality 9. Now we giving the sketch of the proof of theorem. First, we give the proof of only if set YS this form and there and Y0. Since GSD is quasi-so exponentially stable, that is, there exists a constant gamma is greater than 0 such that the inequality. For Y0, the Y20 is equal to 0, we obtain the Y1 is equal to Y1 bar and the following inequality. In addition, for Y10 is equal to 0, we get Y2 is equal to Y2 bar and the following inequality. This completes the only if part. Next, we prove if part. This part includes 3 steps. First step, we given the boundedness of the square number, the difference between Y2 and Y2 bar for this interval by G-Edo formula, exponential martingale inequality, and Borel-Cantor-Lemon and capacity. We get this inequality. Second step, we give the bound of the estimates of the square number Y2 in the interval by triangular inequality. It holds that the inequality 10. Third step, we give the stability of Y2. Now we given an given application. Theorem 2.1 can be applied to the four-order observed design as follows. If H1 to H3 hold with the GSD5, the GSD is quasi-exponentially stable, and there exists phi such that the following system is exponentially stable. We can conclude that filtering error is quasi-exponentially stable. GSD5 is parallel to 6 and 7. Let PS and ES correspond to Y1 and Y2. The proof of this result is derived from theorem 2.1. In fact, system 11 is ordinary differential equation. It is easy to give a sufficient condition, guaranteeing the exponential stability of the 11. Let the output equation 1 be QS is equal to A2, then equation 3 becomes the following equation. According to theorem 2.1, we can deal with the case QS is equal to A2. When field work might focus on larger scale GSD as well as observe best control. This is my literate. Thank you.
Thank you, Dr. Wan Xingyin. Is anyone having any questions? I think there are no questions. Once again, thank you, Doctor, for your presence and presentation. Our next talk will be Dr. Chong Wang Yu from Southeast University, China. Doctor, are you ready with your presentation? Dr. Chong Wang Yu, can you hear me?
Yes.
Okay. Now I'm making you as a presenter now. Please share your screen. Yes, I made you as a presenter now. Please share your screen now. Yes. Can you make it as a full screen?
Good evening. I'm honored to have the chance to address results of my research on this international venture on applied science and engineering. My name is Zhongwen Wu, comes from School of Mathematics, Southeast University. The topic of my paper is multiply T minus alpha stability of fractional switched natural networks with time-varying delays. The outline of my talk is as follows. The first part, I want to introduce the background of this research. The second part is the model description. The third part is the main results. The first part represents the simulation picture of our theory. Finally, a simple conclusion is given. Well, let us move on the first part of this topic. The motivation of these workers as follows. Because of the complexity of actual environment, the connection of the neurons in the networks may change frequently due to the link failure or a new creation of the connection topic in the network. The switching between some different connecting topologies are inevitable. To describe this switching phenomena in the network, switched system is introduced. Switching system are a class of hybrid system and can be found in a communication system, automotive industry, aircraft and air traffic control, and the electric power system. A switching system is composed of several dynamic models and a switching law. Given a switching law, a model will be activated at a certain instance and involved on a following interval of time called devial time. Therefore, switching law is crucially important to the dynamic behaviors of this switched system. For example, this is a continuous time switching system. We can see this picture. It represents the integral order differential equation. The delta is equal to delta t is a piecewise constant function. If you want to know the more information of this title, the title of this paper is Output Tracking Control of Delays Switching System by State-Dependent Dynamic Output Feedback. Next, we can see a switched discrete time natural networks with time variable delays is described as following. We can see this is a discrete time natural networks. The considered system switched from one mode to another mode. The probability transition matrix is as following. This paper title is the synchronization of switched discrete natural networks by coordinated output control with actual filter. In our research on the model discrimination, we consider the following fractional switched natural networks as follows. We can see this is a fractional order differential equation, which alpha is belong to interval 0 to 1. Xit is the state variable. Dixit is greater than 0. AIT and BIXIT are the interconnection weights. IT is the internal input. Tau JT is the time varying delays, and the Tau JT is satisfy this condition. Fj is the activation function. I is the input or binary vector. And the Fj is the Mexican height function defined as. We can see when the U is located in different interval, the FIU is have the different expression. The switching rules is defined as this. This switching rules is different as follows. We can see this is a state delay switching rules. The DIT and the AIJXIT and the BIXIT have the different styles. This following, we have some remarks. In the following, we will describe some definition. A function xt is a solution in the sense of Phillips of system 1. If xt is absolutely continuous on any closed subinterval of 0 to positive infinite and satisfies the following differential in conclusion. And the next definition is a constant vector x is called the equilibrium of system 1, such as this. It is obvious that the equilibrium point in any continuous regions and satisfies the following equation. And the definition 3 is assume x is located in the region D is an equilibrium point of 1 and D is belong to Rn is a positive environment set. Then 1 is called the locality T minus alpha stable. If xt minus xn, the norm is satisfied this equation. Next, we will introduce the main results. When the switching period located in different interval, we have some different discussion. For t is greater than 0 and less than p, let's define some interval. The omega is this. The omega d is this. And then let's describe some interval from the omega d. Let us define this interval is n21, n22, n23, and n24, n25. And then we denote some symbols. When the input balance is less than this equation, and then define this interval is NE. When the index located in different this interval, and let us define this interval is NR. When the index number is located in this interval, we defined this index is N3 and the N4. For in the following, we will introduce the lemma. For I belong to NE, xit will get into this interval and remain there forever. When I belong to N3, xit will get into this interval and remain there forever. When I belong to N4, xit will get into this interval and remain there forever. We will see when I belong to this interval, xit will belong into this interval forever. Next, when it belong to this different interval, we will have different conclusion. We can see for I belong to N21, xit will get into this interval and remain this forever. When I belong to this N22, xit xit T0 is uncertain. That is to say, when xit T0 belong to this interval, then the xit is get out of this interval. Thus, we will see this xit is not belong to this interval. For I belong to N23, xit will get into this interval and remain this forever. When I belong to N24, xit with xit T0 is uncertain. For I belong to N25, xit belong to this interval, and then xit will get into this interval. We can see the xit and the xit T0 is belong to different interval. That is to say, when I belong to different interval, the xit will have different tragedy. Next, we will introduce the theorem. For t belong to this interval, if n is equal to this equation, then there exists 5 N2 equilibrium, and 3 N2 of which are located T minus 4 alpha stable, and the others are unstable. For T is greater than P, let us define this interval, the omega is and the omega d, and then describe some interval from this omega d is define this interval n21, n22, n23, and n24, and n25. Similar to upper discussion, we will have similar conclusion. Next, similar the first part, we will give similar symbols. The NE is input balance and less than this in caution. Let us definite the interval is NE and the N2 and N3 and N4. Next, we will discuss the similar conclusion. When I belong to this interval, xit will get into this interval and remain there forever. That is to say, this interval are positive invariability. The lemma 2 is for I belong to this interval. The xit will have different interval. That is to say, when xit belong to this interval, the tragedy of xit will located in different interval. This conclusion is different for the first situation. Thus, we have the two situations to discuss. And the next, the theorem is for p less than t. If n is equal to this interval, then there exists 5 n2 equilibrium and 3 n2 of which are the locally t minus alpha stable and the others are unstable. Finally, one numerical exam is presented. We consider the following two neurons, the system. We can see the system is a fractional order differential. And then we give the activation function FRU is defined as this. When the U belong to the different regions, the FRU have different constant and different incursion. This is the coefficient matrix when xit belong to different regions. The di and the a11, this coefficient is different, and the switching threshold is satisfied. T is greater than 0 and less than the p. The switching threshold is T is equal to 1. The p is the upper bound of the activation functions. This is the numerical exams. This is the tragedy of xit, and this picture represents the x1 and xit. Xit is the tragedy. Thank you for listening.
Thank you, Dr. Chongwen Yu. Is anyone having any questions? I think there are no questions. Thank you once again, Doctor, for your presence and presentation. Let's move to our next presentation by Dr. Shenweng Li from Southeast University, China. Doctor, are you ready with your presentation? Dr. Sheng Liu. Dr. Lee, can you hear me? Hello. Doctor, can you hear me?
Okay.
Okay, now I'll make you as a presenter now. Please share your screen. Yep, I made you as a presenter. Please share your screen for the presentation.
Hello everyone, I'm Xingyue Li. The title of my presentation is on spectral petroglycan method for solving fractional initial value problems in weighted subleft space. My presentation has the following cell paths. Let's begin with the first pass. We consider the following fractional initial value problems. 1.1, where lambda is a non-negative constant, ft is a given function, and d0 t alpha is the left capital fractional derivative with alpha lying in the interval 0 to 1, defined by the following variable upper limited integral. Due to the weak singularity kernel in fractional derivative definition, the solution of problem 1.1 is weak singular near the origin. Taking into the effect of singularity near the origin, we analyze the regularity of the solution in the weighted subleft space. Firstly, we present the definition of weighted L2 space. Compare with the standard L2 space, there has a weight omega gamma beta x in the interproduct and norm. When gamma equal beta equal 0, we will drop omega from the above notations. Next, we introduce the weighted HS space when S in N plus the weighted subleft space is defined by this. And when S in R plus, the space can be defined via the K-method of interpolation. For S smaller than 0, the space is defined by our duality. Before analysis the regularity in the weighted subleft space, we present the well-posness of the problem 1.1 in standard subleft space and introduce some useful lemmas. Theorem 2.1 is we construct its well-posness of 1.1. And the following are some useful lemmas. Lemma 2.2 present that the regularity for the problem 1.1 with lambda equal to 0. And lemma 2.3 prove that if x in the space H omega 0 alpha s and we have omega 0 alpha multiply phi x in this weighted subleft space. Now we are in position to estimate the regularity of the problem 1.1 with lambda greater than 0 in weighted subleft space. By theorem 2.1, there exists a unique solution U in H alpha over 2. Note that H alpha over 2 is contained in H omega alpha 0 alpha over 2. Hence, by U in this weighted subleft space, we have f hat in this space. By theorem 2.2 with gamma equal beta equal alpha, we have U delta have this regularity. If R greater than alpha over 2, then U tilde in this sublet space. By lemma 2.3, we have U in this space. Then F hat in H omega alpha 0, the minimum will 3 alpha over 2 and 2 alpha plus 1 minus epsilon and r, and U tilde have this regularity. Suppose that after repeating the lifting procedure k times, where k is the least integer such that this inequality holds, we have the state results. Moreover, by the equivalence between problem 1.1 and weakly singularity water integral equation, we can prove that the regularity index rho U tilde can be improved to this index. Based on the regularity estimation established above, we introduce the Petro-Galerkin ultra-weight formulation of the 1.1, like the equation 3.1. And the proof is well posted in theorem 3.1. Then theorem 3.2 and 3.3 present that the U tilde can be bounded by the right-hand term f. Next, we discrete the ultra-weight formulation by using the spectral Petro-Galerkin method. We define the finite dimension space capital U n and capital V n, where P n I is the set rule or algebraic polynomial of degree at most n in I. The special Petro-Galerkin method is given f in this space, and to find un in capital Un such that 3.5 equation holds. Then we can prove that the stability and convergence of the numerical solution. That is, the numerical solution can be bounded by the right-hand term f, and the convergence order of the numerical solution is m, where m is the regularity index of U tet in this weighted sublet space. Next, we present the matrix-free iterative solver. To solve in the discrete system, we use the following fixed point iteration scheme, where the preconditional P is a diagonal matrix, and the initial guess can be chosen by the choose as the numerical solution obtained by a direct method with n equal 8. Resolving forming the matrix A, we compute the matrix product AU by using the fast polynomial transforms and the fast matrix vector product for Topliss dot Hankel matrix. In this part, we give some numerical experiments to verify the theoretical results. In the computation, we take lambda equal 1 since exact solutions are unavailable. We measure the errors in the following sense. There, U reference is the reference solution computed by the same solver but with a very fine resolution. In example 1, we take a smooth enough right-hand term. As the source term f is analytic, the convergence order is expected to be 3 alpha plus 1 minus epsilon. In Table 1, we present convergence orders and errors of the spectral petroglycan method for example 1. The expected convergence order is 3 alpha plus 1 minus epsilon. We find that the numerical results are consistent with expectation. In Table 2, we test the proposed fast iterative solver and find that it has an obvious advantage compared with the direct solver. And in example 2, we take the rough right-hand term. In Table 4, we find that the numerical convergence order confirms the theoretical findings. In next example, we consider the right-hand term with f0 equals 0. In example 3, we consider rough right-hand term, and in example 4, we consider smooth enough right-hand term. The results in Table 5 and Table 6 show that the convergence orders are identical with the theoretical predictions. That's the end of my presentation. Thank you for your attention.
Thank you, Dr. Lee. Is anyone having any questions? I think there are no questions. Let's move to our next presentation by Dr. Jonan Joseph from the University of Girona, Spain. Doctor, are you ready with your presentation?
I can share my screen, please.
Yes. I made you as a presenter now. Please share your screen.
Sorry, wait. Good morning, dear colleagues. In this talk, I will present you some of our results related to iron-based magnetic materials produced by mechanical alloying and also by spark plasma sintering. It is a collaboration between researchers of two universities. Here, the outline of this talk, the main part will be devoted to the experimental part. Yes, we show some results of iron-rich and high entropy alloys with iron produced by mechanical alloying, and also results of some of these alloys consolidated by spark plasma sintering. First, the introduction. The nanocrystalline materials, iron-based, are good candidates for soft magnetic applications. In this case, it is necessary to obtain some properties as low coercitivity, high saturation of magnetization. And also it's very important to control the Curie temperature because the working interval has this limit, the Curie temperature. Okay. Here, in this slide, you can see that on the left, a graph, in this case it is the coercitivity as a function of the grain size. Here you can find that nanocrystalline materials can have low coercitivities, as low as amorphous alloys. On the right, at the bottom, you can see another graph. In this case, it is the crystalline size of an iron-rich alloy as a function of the milling time, and the free collected data are related to free milling conditions. Thus, controlling the processing conditions, we can obtain the same material with different crystalline size, and as a consequence, the materials have different magnetic properties. Low crystalline size, low coercitivity. The production has been performed in our labs by mechanical alloy. We have 3 milling devices. The consolidation was performed in collaboration by spark plasma sintering. Regarding the spark plasma sintering, you can see here the schema of a device. And regarding the materials, the results are linked to iron based and also to iron high entropy alloys, because these materials with the good microstructure are candidates for some magnetic applications, and also can be materials with optimized mechanical properties. Now I began the experimental part of this talk. Here I show you some micrographs that at different milling times of an alloy, electronic microscopy help us to know how the morphology evolves with the milling times, and it's also possible to analyze the particle size distribution. If a microanalysis technique as EDS is also applied, we can obtain also information about contamination and atomic homogeneity of the alloys. To know the microstructure, it's very important to obtain results from X-ray diffraction analysis, because in these systems there are so many phases in incompetence. One example, there are the high entropy alloys. Sometimes the main phase, or the unique phase, it is the BCC, iron rich. Sometimes it's the FCC, and sometimes we can have a mixture of 2 phases. Here, I provide you the diffraction patterns of a high entropy alloy, iron, cobalt, niobium, boron, and silicon, at different milling times, from 0 before milling with the precursors to 150 hours of milling. As you can see here, the final phase, it is the cubic phase centered. The results have been published. From the X-ray diffraction data collected, we can obtain some parameters. We perform the Rietveld analysis, usually with the mode software. This is a free software, and we can determine the lattice parameters. We can also determine the grain size, the microstrain, and also if there are several phases in the same sample, we can determine the percentage of each phase. Here, the lattice parameter evolution with the milling times, and also the fitting parameters typical of the Rietveld analysis. A goodness of fit close to 1 indicates the a best fitting. But the samples that we obtain by mechanical alloying are powders. To consolidate these powders, there are some options: pressing, hot pressing, but one option, it is the spark plasma sintering. Here I show you the piston displacement with the temperature in a spark plasma sintering device, and two experiments were performed. One at 750 degrees and another one at 1000 degrees. In spark plasma sintering, there are technological issues that is necessary to take into account, but the main parameters, it is the temperature of the spark plasma sintering and also the pressure. There are the two main parameters. Here you can see the micrograph and also the X-ray diffraction after a spark plasma sintering of the two samples that you obtain. In this case, you can see that the final phase is different than the original phase. In the first case, in both cases, the main phase is the FCC, but in both cases it is an intermetallic phase, but this intermetallic phase is different. Yes. Here you can see in the micrograph two zones. Each one is due to a crystallographic phase, and the atomic percentage here provided are obtained by microanalysis, EDS microanalysis. Thus, we can check the microstructure because the mechanical answer, the mechanical response, and also the magnetic properties are microstructure dependent. Here you can see the vibrating sample magnetometry results of our samples. In this case, it is the sample millet mechanical alloying EMA 150 hours, the same sample after annealing at 650, and the powdered specimens consolidated by spark plasma sintering at the two temperatures. From the magnetic hysteresis loops, we can determine some parameters as the remanence, and in this case, we show the magnetization of saturation and also the coercitivity. You can see here that high magnetization of saturation is obtained by annealing, but also the results obtained by spark plasma sintering are good enough. Regarding the coercitivity, the lowest value is obtained after spark plasma sintering at low temperature. Thus, sometimes it's not necessary to increase the temperature to attain good properties. We also analyze the surface of fracture by electron microscopy. You can see here both a surface in each case after the two spark plasma sintering processes. The high entropy alloys, as I say before, usually have good mechanical properties. And you can see here the mechanical test performed with the loading and unloading curve. Here you can see the results of the elastic modulus and the hardness as a function of the penetration depth. Another system that we analyze, or another alloy that we analyze, and I show you the results, it is an iron-rich iron-nickel manganese alloy. In this case, it is not a high entropy alloy, it is an iron-rich. I show you here also the X-ray diffraction as a function of milling time with the fitting parameters. In this case, the milling was performed at 130 hours and the spark plasma sintering in free conditions. The same two temperatures than before, with a pressure, and in this case I indicate the pressure, it is 50 megapascals. But the difference it is that at low temperature, we also have an experiment with spark plasma sintering by increasing the pressure, because there are the two main parameters. Here you can see the piston displacement as a function of the temperature. Obviously, the results that we obtain after these free processes are different. The main phase, it is the same, FCC phase, but there are minor changes in the minority phases detected by X-ray diffraction. Here, you can see in this free micrograph the surface after polishing of the free specimens that we obtain after spark plasma sintering. These materials are interesting for the mechanical properties and for the soft magnetic properties. Thus, regarding the mechanical properties, you can see here the hardness obtained by Vickers, obtained for the specimens obtaining after mechanical alloying and spark plasma sintering in the free conditions remarked before, and we compare these results obtained by spark plasma sintering with the results obtained in the same alloy or in an alloy with the same composition produced in a bulk shape by arc melting. Here, there are the results of the hardness. The hardness is higher in the spark plasma sintered specimens, and the best value is not obtained at the highest temperature. It's obtained at the lowest temperature, but increasing the pressure. Some experiments were performed, or several experiments, and here I provide you the mean value and the standard deviation. That sometimes in spark plasma sintering, it is not necessary to increase so much the temperature. Perhaps it's better low temperature to induce not so many microstructural changes, but to apply more pressure. Another alloy that we produce by spark plasma sintering, it is an iron-rich iron cobalt manganese alloy. Okay? Milled during 130 hours, and in this case, the spark plasma sintering has been performed in two different conditions, at two different temperatures. You can see here the image, the micrograph of both specimens. In this case, we play only with the temperature. And we check also the the mechanical response with the hardness. Here, the results obtained in both spark plasma sintered specimens, and in this case, we also compare these results with the results obtained in an alloy with this, or in a specimen of the same composition produced by arc melting. In this case, you can see that also the best result is obtained in the spark plasma sintering specimen at low temperature. In this case, the pressure rate is not different, but the main question is that probably increasing the temperature provokes higher crystallographic changes in the alloy, and thus a loss of the mechanical properties. In this talk, we present results obtained by mechanical alloying and also by spark plasma sintering of these alloys produced by mechanical alloying to consolidate it, but it's not the only technique to produce it. We have collaboration, and we are able to produce also materials by high velocity oxygen fuel spraying. Here you can see an image at the substrate and also the dimensions of the film of the material that it is sprayed in this technique, and you can see also here the result of the magnetic behavior of the powders and of the coating. It is a loss of the magnetization, but it is a slight decrease on the coercitivity. Here you can see a schema of a device of this technique. Well, I finish now with the summary. Thus, mechanical alloying, we think it is an alternative to produce powdered samples of iron-based alloys and also high entropy magnetic alloys. For it, it's mandatory that iron, but also, if possible, cobalt and nickel form part of these high entropy alloys. And the bulk specimens can be produced by spark plasma sintering of these alloys, and it is mandatory to check the mechanical response, the mechanical properties, and also the magnetic behavior for the soft magnetic applications. Yes, And it is very important to know that in a spark plasma sintering, we can play with the pressure and we can also play with the temperature. That's all. Thanks for your attention. Here you can, it is my ORCID number. You can obtain information about my CV and articles, and you can, at my email, you can contact me. You are free to contact me. Thank you.
Thank you, Dr. John Joseph. Is there any questions? I think there are no questions. Thank you, Dr. John Joseph, for your presence and presentation. Let's move to our next presentation by Dr.
Thank you.
Mahabobihin from Superior Tech Coalesce, Portugal. Doctor, are you ready with your presentation? Dr. Atai, can you hear me? Dr. Atai, can you hear me?
Sorry, see, I can hear you. I couldn't recognize my name. Sorry. Yes.
Sir. Are you ready with your presentation?
Yes, actually, I can share my presentation.
Yeah, now
Just
I made
give
you as
me
a presenter now. Please share your screen.
Okay.
Yep.
Okay, let's put it on the presentation mode. Can you see my presentation?
Yes, we can see your full presentation, please.
Okay. So, good morning, evening, afternoon, everyone, everywhere you are. My name is Mahbube Atai. I'm working as a PhD student in Lisbon University, Portugal, and I'm collaborating at the same time with two groups, Serena groups, at which we are doing microencapsulation and we are synthesizing the nanoparticles, and another group, corrosion science and surface engineering, where we are developing a smart self-healing coating, and we are working on corrosion and coating actually. Today I'm presenting one part of my PhD work with the title of Smart Self-Healing Polyolefin Coating for Corrosion Protection of Steel. So let's get started. Okay, as you know, steel is widely used in industry, in construction, automotive, transportation, oil and gas technology, packaging, and appliance due to durability, good mechanical property, recyclability, design flexibility, and competitive cost. However, they are highly susceptible to corrosion, translating for cost. So the cost of corrosion, is about 2 trillion euro in 2018, about 3% of global GDP. So to take full advantage of this material, Okay. I have a little problem in presentation, but okay, we can continue. We need to increase the lifetime of a steel component and reduce also the operation and maintenance costs. To do so, normally applying a coating is a very good strategy. And among the coating, organic coating is mostly used in industry. Self-healing coating, however, defined as a coating with ability to partially or totally repair the defect, can provide us preventing corrosion protection, also autonomous corrosion repair. So, our objective in this work is move from traditional multi-layer coating to single layer thin coating with autonomous and multi-level self-healing ability. In fact, traditionally, we are dealing with this type of coating. We have primer, we have some polymeric coating, we have top coat, depend the type of application, can be TBC or other type of coating. We want to change this coating to a single layer coating, and our strategy is addition of a smart particle to the organic coating. In fact, this smart particle can be triggered by a stimulant like changing in pH or mechanical property. And in fact, we are adding this layer as a capsule or nanoparticles or carrier, and we add these particles to the main layer of coating. In this work, the base coating that we use is polyolefin coating, and the particle that we synthesize to be added to the polyolefin is cerium oxide nanoparticle. For synthesis of cerium oxide, we use cerium nitride hexahydride, and we add ammonia as a catalyst. So we came up with these nanoparticles about with a medium diameter of 50 nanometers. And then we introduce an amine, ethylene diamine, with 4 OH groups and 2 NH groups to these nanoparticles. In fact, we produce a hybrid particles contain organic and organic corrosion inhibitor and inorganic carriers. So after that, a little bit characterization of these particles. We did Raman. In Raman, we have just one intense peak at 461 related to cerium oxygen symmetric stretching, and also we have here XRD pattern. From these two techniques, we can conclude that we have pure cerium nanoparticles that they are crystalline. So happy enough, we loaded these cerium nanoparticles with corrosion inhibitor I showed you before. So here I have FTIR, ATR spectra of nanoparticles, loaded nanoparticles, and corrosion inhibitor. As you can see, in this loaded particle, we can detect all characteristic peaks of corrosion inhibitor and cerium nanoparticle, and we can conclude that we could successfully load the corrosion inhibitor into these nanoparticles. And from TGA, we can conclude the loaded capacity of 33%. So we are happy enough with this particle. Now, what we need to do, we need to introduce this particle to the polyolefin coating. Normally, what we do, we have a coating without any additive as a reference coating to compare the property with this reference. And then we need to prepare several types of coating. Here I prepared 2 coatings with addition of 5 and 1 weight percent of nanoparticles, just nanoparticles to the polyolefin, and 5 and 1 weight percent of loaded nanoparticles. So normally the first method of characterization for us is electrochemical impedance spectroscopy, at which we measure the impedance of the developed coating. In fact, with this measurement, we measure the resistance of the coating against the diffusion of some sort of solvent solution, normally NaCl solution. Okay, so we prepared coating all with the thickness around 30 micron, and then we immersed the coating in NaCl solution 0.05 molar. So here the first results. Here the first result I obtained for reference coating. We have body plot. Here we have impedance at low frequency. As you can see, after 2 days of immersion, we have a very stable coating with capacitive behavior accompanied with the phase angle close to minus 90 degree. It means the coating has a very good quality and good resistance. This coating, reference coating, in this coating, impedance decreasing after 107 days around 2 orders of magnitude. Decreasing the impedance is accompanied with the formation of time constant in these phase angle graphs, meaning that the coating is losing the protection properties. So keeping in mind this graph, we can move to the next graph. This is the coating modified with 5 weight percent of nanoparticles. As you can see, in contrary of the reference coating here, we have still very good capacitive behavior and very high impedance till 94 days, and this capacitive behavior is accompanied with the phase angle always equal to minus 90 degree, meaning that our particles are compatible with the polyolefin coating, and also the developed coating has very good corrosion protective properties. The third graph here, we can see the same graph for the modified coating with loaded particles. So as you can see, again, we have very good capacitive behavior and no phase angle formation here. Normally, we consider this parameter, impedance at low frequency, as a global protection property of the coating. And we like to compare this parameter for these 3 coatings. Here you can see impedance at low frequency for the reference coating during the 130 days. We have descending trend, a little bit here increasing in the value. It's just because the polyolefin by itself has a little bit of self-healing ability, but it cannot last for a longer time. So during the almost 4 months of immersion, this coating is losing the protection property almost 2 orders of magnitude. Here for 4 coating, we modified with 1% of loaded and unloaded particle and 5% of loaded and unloaded particle. The situation is completely different. we don't have any descending trend, and coating are quite stable during the all immersion time. So we are so happy with this coating. We have another way to fit this graph with the electric circuit normally to like evaluate better the situation. We use this circuit for fitting the data we obtained for modified coating, as we didn't have any phase angle developed, and this circuit with 2 time constant to fit the data we obtained for reference coating. So as a result, for modified coating, we have pore resistance around 10 power of 13, which is stable. And for reference coating, this pore resistance showed descending trend as we expected, and the difference is about 4 order of magnitude. Again, with this circuit, we can obtain capacitance of the coating, and low capacitance here for modified coating can tell us that there is just minor change in coating corrosion protective property of this coating. But for reference coating, we have increasing trend, meaning that some conductive path is forming due to diffusion of electrolyte to the coating. With EIS, until now, we can conclude that the global corrosion properties of the coating modified with particle is much better than the reference coating, but it's not enough to evaluate the self-healing ability of coating. To evaluate the self-healing ability of the coating, we have some localized technique that we can evaluate this coating. The first technique is localized electrochemical impedance spectroscopy, at which we make an artificial defect in the coating. Here we can a huge cut around 5 millimeters, and then we immerse this coated sample to the NaCl solution, and then we scan the area included this defect by localized electrochemical impedance spectroscopy. And we normally, in this technique, we like to measure admittance, which is inverse of impedance. So lower admittance, meaning better coating, and meaning active self-healing ability. Okay, this is the data we obtained for the reference coating. We have a huge activity in the 11 hours of immersion, and at the end, we can see that this cut, at this cut, we have corrosion product, we have delamination, and we have opening of this defect. Normally, we like to take a look at these data by this graph. Here, we have the first signal we measure at 1 hour. Here, you can see the most strong signal at 11 hours, and you can see from the first hour to 11 hour, we have huge increase at the signal, meaning that we have very active corrosion activity over this area, and we can see here the result is huge corrosion product on the defect. For the coating modified with unloaded particle, the activity is not so strong, but still we have increasing trend in the admittance during the time, but as you can see, it's not as strong as the reference coating. Also here, the final result, we have still corrosion product, we have still some delamination, but it's like less announced. For the coating modified with loaded particle, the situation is completely different. The first signal we could detect happened after 17 hours of immersion. It means that after during the first hour, after 17 hour, coating could successfully suppress the corrosion activity, and there was not any corrosion activity. In fact, the graph is like this. This is the first signal, then a slight increase in the admittance, and then by the end of immersion, we have continuous decreasing, and this is the final product. No corrosion product over the defect, no, not delamination, and not widening of defect was observed. So normally we call this area at which the activity is always less than the first signal detected as a self-healing zone. So we can conclude here that this modified coating has self-healing ability. But we are still have other techniques to evaluate this modified coating. We have scanning vibration electrode techniques, CEVET, that we evaluated the tree coating with this technique. This is the result we obtained for reference coating. As you can see, in this technique, in fact, we are measuring the current density of ions inside this solution. So here you can see at the beginning, we have cathodic activities for reference coating. Between 13 hours and 20 hours, we couldn't detect any activity, but as you can see, we have delamination. It means that the corrosion activity is underneath the surface. And again, at 25 hours, we detected again a strong cathodic activity. For modified coating, again, the situation was different. This is the same technique. For coating with unloaded particle, we couldn't detect any signal. We detect very weak signal at 25 hours, but it vanished immediately. So as you can see, we didn't have any delamination here. And for modified coating with loaded particle, no signal detected during the all immersion time. So we are happy. It means that we have active self-healing process in our process. Last technique that we use to evaluate the technique is fiber optic dissolved oxygen microsensor. In this technique, we measure the level of dissolved oxygen in the solution. When this dissolved oxygen is decreasing, meaning that we have active corrosion. So the corrosion is consuming actually the oxygen. So as you can see here for the reference coating, we have the very huge decrease in the level of dissolved oxygen. For both modified coating until 20 hours, we didn't have any reduction or very slight up and down. We detect a signal here, like reduction here, which is recovered immediately. It means here we had a corrosion activity, but immediately vanished. So from this technique also, we can conclude that we could develop a good coating with self-healing ability. We can suggest a protection mechanism here. In fact, we took advantage of corrosion to as a trigger for this particle. Cerium oxide nanoparticle known to be pH sensitive. So when we have corrosion, in cathodic side, we have decreasing in pH, and in the anodic side, we have increasing in pH level. At this site, we can have the composition of cerium oxide nanoparticle and have cerium ions, and these cerium ions further can react with OH ions released here in the anodic site. In the other side, this corrosion inhibitor has NH group and OH group, and these groups can react with Fe2 plus and provide us an anodic protection at the anodic site. In fact, these two processes are working together and providing us a very good self-healing ability. In conclusion, we can conclude that these cerium oxide nanoparticle loaded with corrosion inhibitor can provide us an effective corrosion inhibitor for polyolefin. The pore resistance, as I showed you, improved about 4 orders of magnitude by addition of the modified particles. Self-healing ability was evaluated by localized technique, and we demonstrate that the developed coating really has self-healing ability, and the result totally show the ability of this loaded nanoparticle to suppress the corrosion activity and successfully prevent the corrosion. I want here to acknowledge our colleague in Qatar University, Qatar National Research Foundation for financially support us, and CQE and FCT for financial support. If you like to know us better, you can follow us here in the technology platform on microencapsulation and immobilization, and also you can follow us in corrosion science and surface engineering. Thank you so much for your attention.
Thank you, Dr. Mahaboobi. Is anyone having any questions? I think there are no questions. Thank you for your presence and presentation, Dr. Mahaboobi.
Thank you.
Let's take a half-an-hour break for the lunch. Stay connected. Thank you for your patience. Let's start our afternoon session. Our first talk will be Dr. Lucia from University di Bari, Aldo Moro, Italy. Doctor, are you ready with your presentation? Dr. Lucia, can you hear me?
Yes, I can hear you.
Okay,
And so,
now I'm going to make you as a presenter now. Please share your screen.
okay. So, condividi. Can I? Okay, this one. Condividi. Okay. Just a moment. Just to. Okay. So, I should be ready. I hope I should be ready now. Okay, so good afternoon. I am Lucia Catucci from University of Bari in Italy, and today I will present you my work about the use of modified liposomes for the removal of organic dyes from water. These are the topics. Okay, I'm sorry. Okay, these are the topics that we'll explore today together, starting from the theoretical background, then the goal of the study, till to the results obtained. In this work, the organic dye taken into consideration is methylene blue. Methylene blue is a cationic dye used in textile and paper industries, as well as in pharmaceutical application. It is released in water bodies where it is difficult to degrade due to its stable aromatic molecular structure. For these reasons, numerous experimental strategies were put in place to obtain an effective removal of methylene blue from water. The major research efforts are aimed to obtaining materials with high absorption performance and are capable of operating in a very short times. Muscle-inspired chemistry has developed since 1980 concerning the strong adhesion properties of biosus from muscles to a variety of materials. Such properties were attributed to DOPA, so the hydroxyphenylalanine. In particular, dopamine, a derivative that contains catechol and amino groups, can self-polymerize to form polydopamine structure polymer. And in the field of water treatment, polydopamine has found application in the removal of heavy metals and organic pollutants due to its excellent absorbing capacity. PDA, in fact, has numerous catechol and amino groups, as well as aromatic moieties that can bind both organic and inorganic pollutants through different types of interactions, such as hydrogen bonding, electrostatic interaction, and so on. A variety of PDA-based adsorbent material have been designed and developed. However, this absorbent made only of PDA generally exhibit low absorption capacity and poor stability. So, in this work, phospholipid-based liposomes were used as templating agents to obtain liposome PDA microspheres to realize a novel and biocompatible and efficient absorbent material for methylene blue. Liposomes are vesicles derived from the spontaneous self-assembly of phospholipid molecules in aqueous solution to give rise to a structure in which are present an hydrophilic core and hydrophobic bilayer. liposomes find application in a wide variety of fields, such as protein reconstitution, drug delivery, vaccine development, and templating agent for nanostructured material. In this work, liposomes were used as a templating material to obtain spheres, microspheres of polydopamine that are able to absorb methylene blue. Liposomes were prepared with extrusion method using membrane with a porosity of 200 nanometers. The coverage with polydopamine was realized adding dopamine hydrochloride to the liposome and leaving to react at pH 8 under stirring and also aerobic condition. The prepared liposome PDA microsphere were characterized by transmission electron microscopy, dynamic light scattering, and infrared spectroscopy. The transmission electron image show a liposome is low contrast and has a spheric structure with an average dimension size diameter of about 200 nanometer. After 24 hours of dopamine polymerization, the transmission electron image revealed higher contrast spherical nanostructure with an average diameter of 400 nanometer that were ascribed to liposome PDA microsphere. The dynamic light scattering measurement confirmed the formation of a shell around the liposome during the polymerization. The successful coverage of liposome with polydopamine was confirmed also by the presence of the signal of both components in the infrared spectra of this system. Okay. So then we studied the absorption properties of the system prepared. First of all, we evaluated the effect of pH on the absorption processes on the absorption of methylene blue properties. We observed that the absorption capacity progressively increased with increasing the pH and reached the highest value at pH 8, where the zeta potential was strongly negative, and this confirming that electrostatic interaction is the main mechanism that drives the dye absorption phenomena. The slight decrease in absorption capacity observed at pH 10 could be due to the fact that the polydopamine shell in a strong basic environment has been slightly broken, or there should be the possibility of a dye aggregation phenomena. The effect of methylene blue and liposome PDA microsphere concentration was also investigated at pH 8. The first graph reports the variation of absorption capacity as a function of contact time and initial dye concentration. it is possible to observe that for all methylene blue initial concentration, the QT values undergo a dramatic increase already within the first minute. Subsequently, the absorption progressively slowed down until equilibrium was reached. The absorption equilibrium time was found to be about 35 minutes, and no significant change in QT value occurred over the next 55 minutes. The absorption process appeared to be dependent on the initial concentration of methylene blue. In particular, the QE value progressively increased with increasing dye concentration. This can be explained considering the fact that at higher concentration of the dye, the possibility of a collision between the dye molecules and the absorbent is statistically more probably, thus increasing the absorption. The second graph instead reports the variation of absorption capacity as a function of contact time and mass of absorbent. In this case, we observed that the absorption capacity decreased with increasing the concentration of microspheres, but we are able to obtain a very high absorption capacity that was about 395 milligram per gram of microsphere, a value higher than those of similar PDA-based absorbent material reported in literature. So, in the end, we obtained with this system a removal efficiency up to 96%, so very high. We performed also a kinetic study. Kinetic parameters, in fact, provide important information on the dynamic of the absorption process. We used the pseudo-first order kinetic model and the pseudo-second order kinetic model. The pseudo-second order model clearly fits better the experimental data, possessing R² higher. Moreover, this kinetic model provides a calculated QA value very close to the experimental one. These outcomes suggest that the absorption process of methylene blue onto liposome PDA microsphere is controlled by chemisorption. The absorption isotherms were studied also in order to obtain information on the surface properties of the absorbent material and then on the behavior of the solid solution system. The experimental data were fitted by two different models, the Langmuir isotherm model and the Freundlich isotherm model. Langmuir is a well-known isothermal absorption model for studying the solid solution system, and it is based on the assumption that the absorption process involves the formation of a monolayer and that the surface of the absorbent material is homogeneous. In contrast, Freundlich model predicts that the absorbent surface is heterogeneous and that a multi-layer absorption process takes place. As it is possible to see from the slide, the Langmuir isotherm model better describe our experimental data. Moreover, we calculated also the specific surface area of our microspheres and obtained this value that is very high and that can justify the high absorption performance of these liposome PDI microspheres. The effect of temperature on the absorption of methylene blue on this microsphere was studied through in a range of temperature. As reported in this graph, it is the absorption capacity increasing the temperature. This suggests that the process is an endothermic process. We utilized the Van 't Hoff plot. We were able also to calculate the variation of enthalpy and entropy, as well as, of course, the variation of free energy. And the value obtained confirm an endothermic process, and also the variation, a positive variation of entropy reflect the affinity of the adsorbent material for the methylene blue and suggest that the degree of disorder of the solid-liquid interface increase during the interaction between the dye and the microspheres. Okay. Absorption experiment in solution containing salt and in simulated wastewater were conducted to evaluate the applicability of this liposome PDA microsphere in real context. The experiment showed that the absorption capacity of liposome PDI microsphere towards methylene blue remained high even in complex solution, indicating the possibility of their use in real context. Afterwards, absorption and desorption experiments were carried out to assess the regeneration and stability of liposome PDA microsphere for methylene blue uptake. As shown, the sorbent retain good absorption capacity efficiency at more than 90% of the original value after 3 cycles. So, in conclusion, we can say a new polydopamine-based adsorbent material was prepared for water remediation. This liposome PDI microsphere showed a very good absorption capacity, a good performance also in real matrix, and excellent reusability of the system. Thank you for your attention.
Thank you, Doctor, for your presentation. Is anyone having any questions? I think there are no queries. Let's move to our next presentation by Dr. Arizo. Yeah, bye-bye.
Yes, can you hear me?
Yes, I can hear you, Dr. Arizo. From
Okay.
Fedris University of Mahdi from Iran. Doctor, are you ready with your presentation?
Okay.
I made you as a presenter now. Please share your screen.
Okay. Topic of this presentation is comparison of damage evolution during
Can you
thermal
make it as a
cyclic
full screen?
fatigue. Yes, I did. Okay. Just a moment. Okay, there is a problem. No.
You can see in the PPT presentation below that you'll be having one slideshow option in that PPT. Towards the right side, below that PPT.
Yes, I know, but I can't see it because
you can minimize that GoToMeetings app.
Okay, I did it. It's okay?
Yes, you can.
Is it okay?
Yeah, yep, now it's perfect. Please continue.
Okay.
Yep.
Okay. The topic of this presentation is comparison of damage evolution during thermal cyclic fatigue in nanostructured, micro, and hybrid compositionally graded layer TBCs. The contents that we are investigated is introduction, materials and methods, results and discussion, and conclusion. Thermal barrier coatings are commonly applied to increase the efficiency and extend the life of metallic parts used in gas turbine. The efficiency and performance of gas turbine engines have been enhanced by using thermal barrier coatings. TBC stands for thermal barrier coatings, are applied as coatings on turbine components or aircraft engines in order to materials protection against high thermal oxidation and hot corrosion. Common double-layer TBC systems consist of an alloy bound coat and a ceramic top coat. You can see the schematically figures that show the thermal barrier coatings, I mean double thermal barrier coatings. As you can see, it's substrate, bound coat, and top coat. Bound coat is used as an interlayer between the top coat and the substrate. These coatings are often chosen from M-poly group coatings. M letter identified nickel and or chrome. Yttria stabilized zirconia is a good ceramic material candidate for application in the TBC systems. During long-term high-temperature exposure, thermally grown oxide layer forms at the top coat-bound coat interface. In the schematic figure of TBC substrate, bound coat TGO, which stands for thermally grown oxide, and top coat can be seen. Top coat and bound coat have some properties and duties which are listed in this part. The properties and duties of bound coat are improve the oxidation resistance of metallic substrate, promote adhesion of ceramic top coat to the substrate, reduction of thermal expansion mismatch stresses between top coat and metallic substrate. And the properties of top coat are low thermal conductivity, high coefficient of thermal expansion, stability in the desired temperature range, and finally good resistance to erosion. One of the main methods for preparing bound coat and top coat is atmospheric plasma spraying. The CTE, coefficient thermal expansion difference between metallic and ceramic layer of TBC, produces a stress at the interface of metal ceramic in the high temperature application. Thermal cycling fatigue is one type of thermal cycling test. TCF occurs as a result of start and stop of gas turbine. It results in severe conditions such as bound coat oxidation, thermal shock, and can severely affect the coating lifetime. Compositionally graded layer coatings have been proposed in order to decrease thermal expansion mismatch between ceramic and metal layers of TBCs. These coatings can be obtained by gradual change in composition of neighboring layer. The first group, first of all, I should explain about these coatings. You can see 4 figures here. The first group of TBC is double layer TBCs. It has just bound coat and top coat. The second one is gradient layer TBC. It means 3 gradient layer TBC. You can see bound coat, second gradient layer, and third gradient layer or top coat. The third group has 4 layers and the last one has 5 layers. It means that we can have different layers in compositionally graded layer coatings. Another solution for improving the oxidation resistance of TBC is using nanostructure coatings. Nanostructures coatings exhibit a bimodal microstructure due to presence of semi-molten nanostructure powder that is named nanozones, which is embedded in fully molten powder. The nanozones are obtained using a porous nanostructure feedstock which is only partially molten during deposition by air plasma spray process. These pictures shows that 2 parts. You can see nanozones that is indicated by blue arrows and the matrix. In this research, 2 kinds of TBC powder were used. One is micro-YSZ, the brand is Medco 204 NSG, and the other one is nanostructured YSZ, the brand is Nanox S4007. And the powder which is used in for bound coat was nickel chrome aluminum yttrium. The brand is MDry 962. Field emission image of the micro and nanostructure YSZ are shown in the following pictures. You can see in the part A, the figure, part A shows nanostructure, this picture, nanostructure YSZ powder, and part B is the same powder in a higher magnification. In part C, you can see the micro YSZ powder, and in the part D is the same powder, micro powder in higher magnification. You can see the difference between nanostructure and micro YSZ in higher resolution. 3 groups, in this research, 3 groups of gradient layer thermal barrier coating were produced for development of the TBC. The mixture of nichroli and YSZ powder were plasma sprayed. Different mixture of bound coat and top coat powder were plasma sprayed. We have 5 layers. In the first layer or in the bound coat, we have 100 weight% nichroli. In the second layer, we have 75 weight% nichroli and 25 weight% YSZ. Third layer composed of 50 weight% nichroli and 50 weight% YSZ. Fourth layer composed of 25 weight% nichroli and 75 weight% YSZ. And the last layer or top coat has 100 weight% YSZ. As you can see, YSZ powder increased until it reached to 100 weight% in the top coat. It is similar for all 3 groups. The only change is the kind of TBC. You can see three schematic figures. The first one is micro compositionally graded layer TBC that we use a micro YSL for TBC powder. And in the second one, we use nanostructure YSL powder. In the middle one, or hybrid compositionally graded layer TBC, we use both kind of TBC powder, nanostructured and micro. Samples were thermally cycled between 100, after we prepared the samples thermally cycled between 100 centigrade and 1150 centigrade with a dwell time of 1 hour at high temperature. The specimens were cooled using compressed air for about 10 minutes, then reaching a minimum temperature, 100 centigrade. The test was continued until the sample failed, and the failure criterion was considered when 20% of coating was damaged. The thermal cyclic reed was equipped with a camera for recording of cooling process. The stored images were checked carefully after each cycle. As a sprayed microstructure of compositionally graded layer coating is shown in following figure. You can see good interface between substrate and bound coat and different layers without any crack. Here is bound coat and here is top coat. Between this bound coat and top coat are other gradient layer that is shown by second, third, and fourth. In order to display the distribution of YSZ unequally in compositionally graded layer, EDS mapping was performed. The EDS result of TBCs show top coat with elements of ceramic YSZ, bound coat with elements of the alloy, nickel, chrome, aluminum, and also reveals the distribution of main elements of the alloy and ceramic. You can see this here, aluminum, chrome, nickel, zirconium, and yttrium. Thermal fatigue lifetime of nanostructured micro-hybrid compositionally graded layer and micro one show that the lifetimes of nanostructure is 50, the lifetimes of micro is 31 and the lifetimes of hybrid is 20. The nanostructure exhibits the highest TCF damage resistance. It should be mentioned that the furnace was sending signal directly to camera during the start of each cooling cycle. Video camera recorded image automatically. Part A in this figure displays the recorded image at the beginning of cooling cycle, and Part B in this figure shows recorded images after 29-second cooling. Region 1 here, Region 1 indicates that the coating is still intact. Region 2 in gray indicates delamination and region 3 indicates spallation. Damage observed from the video camera is then estimated by measuring the delamination and spalled region as damaged area. TGO that I speak about it, thermal ground oxide, is formed as a result of bound coat oxidation during high thermal exposure. In compositionally graded layer TBC, metallic parts of graded layers as long as bound coat are oxidized. Thus, oxide layers are formed around the metallic faces. You can see here, I show it here, its bound coat and its gradient layer. You can see TGO here and here in gradient layer around the metallic parts of graded layers. So you can see the map here that show the elements chromium, aluminum, yttrium, zirconium, and oxygen and nickel distribution of different elements to each other. Alloy oxidation has been known as a major cause for delamination of TBCs during high temperature exposure. Aluminum forms protective alumina scales as long as it is enough in the bond coat. Depletion of aluminum causes formation of non-protective oxide. These oxides are mixture of chromia and spinel formed at the interface of alumina ceramic. Therefore, TgO is composed of alumina and non-protective oxides. You can see elemental maps of a part of graded layer of micro-compositionally graded layer TBCs after TCF test here. TgO layer are formed and the composition of this oxide layer can be detected by noting to the distribution of elements. Here is nanozones and TgO layer can be seen in this figure. You can see here nanozone, it's a nanozone and a ceramic part, and it's a bond coat and metallic part. You can see that this gray parts, it is TgO layers, and if follow the mapping, you can find the composition. It's aluminum, oxygen, nickel, and chromium. Growth of non-protective oxide leads to further local volumetric, which induces extra tensile stress in the ceramic region, and as shown in following figure, cracks can initiate and propagate within these regions. You can see this crack that propagate in this part. Okay. This picture is belong to micro-compositionally graded layer TBC after TCF test. Growth of non-protective oxides leads to the further local, buckling delamination occurs at the interface of top coat for gradient layer. In the micro-compositionally graded layer TBC, delaminated layer can convert to a spallation region where longitudinal cracks overlap with transverse cracks or edges of the samples. In nanostructured coating, as you can see the figure here, this figure is also after TCF test, and you can see that spallation could happen simultaneously with delamination. Bulking delamination occurs at the interface of top coat for gradient layer. Nanozones are detached from the matrix during cyclic thermal exposure because of the weak adhesion between nanozone and the ceramic matrix. Detachment or broadening during longer thermal cyclic fatigue. You can see it in two pictures. This picture is belong to video camera, and this picture is microscopic pictures that is taken by SEM. Delamination occurs in the interface of top coat and four gradients layer in hybrid compositionally graded layer. It is also in bottom gradient layers. Separation of top coat is shown in part A in this figure. You can see it. And also cracks are initiate and propagate in the gradient layers. So separation of these layers occurs, and it shows in these pictures. And the conclusion, the nanostructure compositionally graded layer TBC exhibited the highest delamination resistance. Presence of nanozone leads to postpone the initiation of crack and result in higher number of cycles. According to the video monitoring, the first signs of TCF damage revealed in hybrid compositionally graded layer TBC, micro compositionally graded layer TBC, and nanostructured compositionally graded layer TBC respectively. The most percentage of the damage was occurred toward the end of the coating's life. Thank you.
Thank you, Dr. Arizo, for your presentation. Is anyone having any questions?
Excuse me, I have a question.
Yes, you can, please.
Thank you, Arzu, for your very nice presentation. I have a question regards the preparation, because you mix actually thermal barrier coating, which is ceramic, with nichrally, which is actually a metal. My question is, did you have any problem with melting temperature? Because what I understood, maybe I'm wrong, but you increase the temperature to have the melted powder, and then you apply it on the substrate. Or I'm wrong.
Yes.
If you don't mind, please explain me
No,
a little.
the process. Continue, please. Sorry.
No. Go ahead.
Okay. The process for deposition of TBC is APS, is air plasma spray. The temperature is very high in this process. You mean we mix the powder with each other, TBC powder and metal powder mix with each other, and then plasma spray on the coatings, on the substrate. I'm sorry.
So I mean, because and because you mix the powder and you use APS and you use the same temperature, the same process, so you don't have any, for example, for evaporation of metallic phase that may produce some defect.
No. It don't have this problem in TBC in a compositionally graded thermal barrier. The only problem that we have is about the metallic parts when in high temperature, the exposure to high temperature, metallic parts that are next to ceramic parts, they are oxidized sooner than bond coat. And it's the only problems. There is not problem for process, you know. The only problem is after that when we want to oxidize. But for this reason, because we want to decrease this problem, we use nanostructured coating. Presence of nanozones decrease this problem. I have three paper that explain about that. If you want, you can read it.
Okay. Thank you. Very nice work. Thank you, Arzu.
Welcome.
Thank you, Dr. Mahbub, for your question.
Thank you.
Any more questions? I think there are no questions. Thank you once again, Dr. Arizo, for your presence and presentation. Let's move to our next presentation by Dr. Nataraj Mishra. But due to some emergency and his busy schedule, he was unable to attend today's webinar. But he has sent us his recorded video presentation. If you have any queries regarding that, you can mail to the concerned program manager. They'll be responded to you. We'll be sharing his recorded video presentation from our screen.
Engineering at UPES in India. My qualification vibration control, controlling flexible oscillator using passive and active damping control methods. Now this is the first part of the video. I am Dr. Nataraj Mishra. I am working as assistant professor in the Department of Mechanical Engineering at UPES in India. My qualifications are PhD in flexible robotics from IIT Delhi, MTech in robotics and automation, and I am graduate in mechanical engineering. My dissertation topic was dynamic modeling and control of two-link flexible arm robotic manipulator. At present, I am looking for collaboration with researchers like you, with whom I can do some quality research in the areas of robotics, controls, vibrations, etc. My contact details are there on the screen. My mentors are late Professor B.C. Nakra and Professor S.P. Singh. They guided me during my PhD work at IIT. Let us come to our topic, vibration control of the flexible manipulator. So in this presentation, I am going to discuss the vibration control of a two-link flexible manipulator. So the manipulator is having two revolute joints. Here, both active and passive dampings are considered for vibration control of the links. Both bending and torsional vibrations are considered. The methodology adopted include mathematical modeling of the flexible manipulator, inclusion of scholastic damping, inclusion of piezoelectric damping, and then simulation. In this diagram, you can see a two-link flexible manipulator. So there are two planes. One is plane of bending deformation, and the second is plane of torsional deformation. The plane of bending deformation is characterized by XY axis, and the plane of torsional deformation is characterized by ZY axis. Actually, this plane of torsional deformation is the side view for this plane of bending deformation. Now here you can see that there are three different types of axes: XY axis with no subscript, X1 Y1 axis, and X2 Y2 axis. The XY axis is the global reference frame. X1 Y1 axis is the moving frame attached to link 1. X2 Y2 axis is the moving frame attached to link 2. The link 1 moved with angle θ1 with respect to the fixed frame X1 XY. Similarly, the link 2, it moves with an angle θ2 with the moving frame X1 Y1. You can see here that θ2 is the rigid motion of link 2 with respect to X1 axis. Similarly, θ1 is the rigid motion of link 1 with respect to X axis. Now, besides having these two rigid motions, the links of the flexible manipulator exhibit deformations also. The deformations are governed by the variables W1 and W2. And these deformations are there in the local frame of references of the given links. Similarly, in plane of torsional deformation, we have twisting motions phi1 and phi2. Phi1 is the twisting motion of link 1 in its own local frame of reference. Similarly, phi2 is the twisting motion of link 2 in its own local frame of reference. Now after this, the links were discretized using finite elements. Space frame finite element was used. In this figure, at present, two finite elements are used for discretization. You can see here that there are three nodes, node 1, node 2, and node 3. Each link consists of one node. You can divide one element. You can divide into more number of elements also to get better results. So each node is having 6 degrees of freedom, 3 rotational and 3 translational. After that, we get the matrix equation which defines the dynamics of the flexible manipulator. The first square matrix consists of inertia terms, which, where the term M is written. So the M represents the inertia. The subscript R represents the rigid and subscript F represents the flexible. So MRR is the matrix which characterizes the rigid motion of the manipulator, theta 1, theta 2, and MFF. Let's see here, MFF. It represents the mass matrix corresponding to the flexible motion of the manipulator. And MRF, it represents, and MFR, they represent the coupling between the rigid and flexible motion. Similarly, the matrix C, it represents the damping matrix and gyroscopic matrix. K represents the stiffness matrix. H represents the centrifugal and Coriolis torque matrix, and G represents the gravitational force matrix, and FR represents the torques which are applied at the joints, and FF represents the torque which are responsible for causing flexible motion or elastic deformation. So the present study, the values of FF are taken as 0. Only joint torques are used, that is FR. So there are two joints, so two joint torque values are provided. Now in this equation, capital N represents the number of rigid degrees of freedom. So here in this case, there are two joints, so this capital N is equal to 2. That is theta 1 and theta 2. And small n represents the number of elastic degrees of freedom. It depends upon the number of elements into which we have divided our links. Now the constitutive equations for piezo material will be described first. First of all, we shall explain this phenomenon of piezoelectricity. So these equations are taken from a book by Andrew Cremont. For sensing, we have this equation, and for actuation, we have this equation. So these equations, they give relationship between stresses which are produced in the geomaterial and the applied electric field and displacement. And you can see that these are the constant D31, D32, D31, D32 here. These are the piezoelectric constants. Epsilon represents the strains in the piezoelectric material. Sigma represents the stresses. This capital E, it represents the electric field vector. And this capital D, it represents the displacement. Now a smart beam is shown here in the figure. You can see that the piezo sensor and piezo actuator are applied. Piezo sensor senses the vibration from the beam and it gives it as a feedback to the piezo actuator. So piezo actuator obtains the voltage, and this voltage is converted into some load and moments which are applied to the beam at the point where, or at the location where piezo actuator is applied. It helps in curbing down the vibration. We can see that this piezo actuator can be modeled as a distributive load which is time varying. Now the piezo sensor, the voltage generated by the piezo sensor can be expressed by this equation. Here, this small w represents the deformation of the beam. Dot represents differentiation with respect to time, and dash, this dash represents differentiation with respect to x, that is space. Now using integration by parts, we can expand this integral term. For the sensor, we can take bpx. Bpx represents the width of the piezo sensor constant, and for actuator, we can take this bp double dash x as constant. That is the second derivative of width of the piezo actuator with respect to distance x as constant. Now this is the complete expression for piezo sensor. You can see it depends upon both time differential of deformation, that is a rate of change of deformation, and here w dot dash represents the rate of change of slope of deformation. Now the voltage generated by the sensor is fed back to the actuator. Actuator generates the distributive load, and this distributive load is converted to the forces and moments which are applied by the piezo actuator by this equation, and this comes from the finite element theory. Now this is the final equation for the vibration of the beam, and Fe represents the active force which is generated by the piezo actuator, and M represents the mass matrix, and K represents the stiffness matrix, and this Q represents the vector of degrees of freedom. Here this Q represents the elastic degrees of freedom. Now you can see here that the location of actuator and sensor, it plays important role. We'll see later on this thing. So in this diagram, you can see that Q1, Q3, Q4, Q5, Q7, these are translational degrees of freedom, and these represent the deformation of the beam, while Q4, Q6, Q8, they represent the slopes of the beam. Now active force and active damping, they can be used analogously. Either you can use active force or you can use active damping. So instead of using active force, we can convert it into some damping force. So accordingly, we can modify our equation. The formulation of all these equations, they are provided in one of my research papers, which I have given reference to the last part 2 of the video. Now in this diagram, you can see the arrangement of sensors and actuators on the flexible links. You can see here that actuator A and sensor S, these are applied at suitable locations on the links. Now, when actuators and sensors are applied at different positions, then it is known as non-collocated arrangement of sensor actuators. And when actuators and sensors are applied at the same position, then they are known as the collocated arrangement of sensor and actuator. The diagram here, it shows the collocated arrangement of sensors and actuators. Actually, from the literature, it is found that this collocated arrangement gives better vibration control. But non-collocated arrangement can also be used for better vibration control, provided damping is high in the system. So, in order to increase damping within the system, viscoelastic material can be pasted over the link. Now, after discretization, the local mass matrices and the local stiffness matrices were obtained, and these were assembled together to obtain the global mass matrices and global stiffness matrices, similarly global load vectors also. Now here, you can see an important term, LPF. This LPF, it is a transformation matrix. It gives the relationship between the rigid motion and the flexible motion. So that is, it transforms motion from universal frame of reference to the local frame of reference, or vice versa. So for link 1, it depends upon theta 1, and for link 2, it depends upon both theta 1 and theta 2. So since the configuration of manipulator is changing at every instant of time, so this transformation matrix is also changing at every instant of time, and hence the global mass matrix, global stiffness matrix, and global load vectors, they are also changing at every instant of time. That's all in the first part of the video. The second part of the video on vibration control of a two-link flexible manipulator using passive and active control methods. Now, in the previous video, we have seen the modeling of flexible manipulator, modeling of the smart beam using piezoelectric crystals. There we used sensors and actuators. Now, the sensors and actuators can be used either in collocated arrangement or in non-collocated arrangement. For non-collocated arrangement, it is required to have high damping within the system. Now, in order to increase damping within the system, some structural damping or passive damping means have to be incorporated. So the first one is to incorporate viscoelasticity. So viscoelasticity can be modeled by using various models like Maxwell model or Kelvin-Voigt model, 3-element model, and we can increase the number of springs and dashboard to yield some other models. And in each of these models, it is required to establish the relationship between stress sigma and strain epsilon, or force F and deformation U. So if we are able to represent these models in this form, then we can perform the simulation and study the viscoelasticity. Now, based upon that, some damping matrix was formulated. I have discussed the mass matrix and stiffness matrix and load vector in the previous part of the video. Damping was not there. So by using viscoelasticity, damping can also be included. So these matrices, they give the local damping matrices. Now, global damping matrix can be found out by using this LPF. I have discussed this LPF depends upon theta 1 and theta 2. Theta 1 and theta 2 are the joint variables which represent rigid motion of the manipulator. Now, as I said in the beginning that both bending and torsional vibrations are included. Until now I was explaining the bending vibrations. Now, torsional vibrations were also modeled. You can see here that this is a beam and piezo actuator is placed over it, and the governing equation was obtained. The derivation of this equation is given in one of my research papers, which I have provided in the reference section. Here Im is the mass moment of inertia of the beam, and J is the polar moment of inertia, and capital G is the modulus of rigidity of the beam. And you see here that the constant piezoelectric constant D24 is used here.
Hello.
So now, since shear stress, this torsional element, it applies shear stress on the beam, and shear stress is always complementary. So this equation gets modified as below. Now I will explain the simulation results. Before that, let us have a look at the physical parameters. Here, length of links, width of links, thickness of links, flexural rigidity of the links, density of links are provided, and joint torques values are also provided. For joint torques, square wave signal is used as a joint torque. The frequency is taken as 10 Hz for each of the joint torques. At joint 1, the amplitude of the square wave is 0.05 Newton meter, while at joint 2, it is 0.01 Newton meter. Simulation time of 0.1 second is taken, and step size is 10⁻⁻⁶ seconds. OD45 is the solver. Here, 2-node frame element is used. And these are the physical properties of the viscoelastic material, which is rubber, and physical properties of piezoceramic, which is PZT, lead zirconate titanate, and area of cross section of piezoceramic is this. Now, first of all, let us have a look at the effect of viscoelastic damping. So this graph compares between undamped and viscoelastically damped system. So this is the tip vibration of the flexible manipulator. You can see when undamped, when there is no damping, the graph is shown by red color. The vibration levels are high, and when viscoelastic damping is used, then you can see that there is a remarkable improvement in the vibration levels at the tip, and which are shown by blue color. Now next, this graph, it shows the comparison between collocated and non-collocated control at a specified values of gain. While using active control, proportional derivative control was used. There are various types of control methods. PD control method is a common control method, so that has been utilized, and there we require proportional gain and derivative gains. So KP stands for proportional gain and KV stands for derivative gain. So low gain values are used here. So you can see here that located control, which is shown by blue color, it is effective in controlling the vibrations, as is found in the theory also. Now this diagram shows the comparison between different values of gains used during active control. So here from this diagram we can see that at low values of control gains, the tip vibration response is better than when high control gains are used. By using high control gains, probably the active controller or it is inducing more vibrations, can be said. So for the present study, the low control gains were suitable for controlling the vibrations of the flexible manipulator. The low control gains are characterized by this blue color. Similarly, now there is effect of hybrid damping. Hybrid damping means that both viscoelastic damping and active damping are used. So you can see that the active damping results are shown by red color, while hybrid damping results are shown by blue color. You can see here that when both active control and viscoelastic damping are used, better results are used, and this is obvious, and this is in conformity with the results as provided in the literature. Here the effect of torsional vibrations are shown. Only active damping is considered here. You can see that in case of undamped response, see the response, it increases after a certain time and amplitudes are increasing. But in case of active damping, you can see that the amplitude of vibrations, it becomes constant. It's constant throughout. By using viscoelastic damping, we can further reduce these amplitude of vibrations. So torsional vibrations are also curved in this study. Now let us look at the effect on eigenvalues. So first of all, we shall look at the undamped system. What is the effect of increase in the number of finite elements? When we increase the number of finite elements, that is when 4 finite elements are used. 4 finite elements means that 2 elements per link are used. So total 4 finite elements are used. So these are the first frequencies of first 3 modes of vibration. And when 8 finite elements are used, that is 4 finite elements per link. That case, you can see the frequencies of first 3 modes. So this forms a part of the convergence study. Whenever we use finite element method in our study, it is necessary to perform the convergence study. The convergence study helps us to know that how many number of finite elements are adequate to give obtain correct results. That is by in finite elements, by increasing the number of elements, we can obtain different results. So how many number of finite elements can be used? So this knowledge is required. So hence, convergence study is very much important. Then now you can see that in undamped system, the lowest harmonic is 2.1 Hz. But now when viscoelastic layer is used, when it is pasted throughout the links, throughout the length of the links, the first harmonic, if you look at the first harmonic, it changes to 3.22 Hz. Similarly, other modes of vibration, that is other frequencies of second mode and third mode, they also change with the incorporation of viscoelastic layer. Now when piezoelectric layers are incorporated, then you can see that now these piezoelectric layers, they are applied intermittently. They are not applied continuously over the beam. That is why you can see that there is a small variation in frequency in the application of piezoelectric. But still there is a change in the frequency. And when both piezoelectric and viscoelastic layers are used, then also we have change in the fundamental frequency of the beam or of the links. So while using either active control or passive control, it is necessary to take care of the frequency variation which they are causing into our system.
Yes. Are you logged in from? Yes. Are you logged in from?
Furthermore, it is also found that when we use different values of controller gains like proportional gain or derivative gain, they also alter the frequency of the structure. The conclusions are that the piezoelectric actuator applies time-dependent turning moments on the portion of flexible link where it is twisted. The proportional derivative-based feedback controller is designed for obtaining the positional accuracy of the flexible manipulator. The results show that the presence of viscoelastic damping effectively reduces the higher harmonics of vibration. And it is found that collocated control is more effective than non-collocated control in curving the vibrations. It is advisable to use hybrid damping for vibration control of the flexible manipulator, where lower values of controller gains can be used to produce the same effect. The passive viscoelastic material is very effective for higher frequency components of vibration. Novelty of the present work lies in control of both torsional and flexural vibrations through the application of passive and active damping methods to the non-inertial frames represented by the manipulator links. Now, for references and other details, you can refer to these two papers. They have been written by me in collaboration with Professor S.P. Singh. And you can refer to, for references, you can refer to the reference section of these two papers. And for mathematical details, you can refer to these two papers. At the end, I would like to acknowledge my organization UPES, which provides facilities to its employees in the form of good HR policies for doing research work. My colleagues at UPES, with whom I used to discuss my research work. My research fellows and staff at Vibration Laboratory at IIT Delhi. And intern Mangalam Mishra, who helped me conduct my experiments at IIT Delhi. Thank you.
Thank you, Dr. Thank you, Dr. Natras Mishra, for his presentation. Is anyone having any questions? You can question that in the chat box. I think there are no questions. Let's move to our next presentation by Dr. M. Srinivasan from Annamala University, India. Doctor, are you ready with your presentation?
Yes.
Okay, now I'm going to make you as a presenter now. Please share your screen.
Okay.
Yeah.
Do you visible my slide, ma'am?
Yes, we can see your present.
Okay. Yes. Is audible, ma'am? Okay. Good evening to all in India.
Sorry for the interruption, doctor. Please share
Yes,
your
yes,
screen. We
yes.
are unable to.
Not visible?
No, it's not visible.
Okay. Okay, you one second I will try.
Doctor, we are unable to hear your voice also. Dr. Srinivasan, are you there? Maybe he's having some technical issue. Let's wait for 2 more minutes to respond. Dr. Srinivasan, can you hear me? Dr. Srinivasan.
Yes,
Perhaps
this
we have
audio
to
is clear.
do.
Yes, we can hear your voice now. Dr. Srinivasan, can you hear me? Dr. Srinivasan.
Yes, no audio is there.
Yes, now audio is okay.
Yes.
So please share
Ah,
your screen.
okay. Okay.
Doctor, please share your screen.
Oh. Now I share that.
Please share. I already made you as a presenter. Please share your screen. You need to unclick that screen share option so that we can see your presentation. Please click on that screen share button.
Screen share. That is no screen share. Screen and camera are being shared.
Before that leave button, you'll be having screen option. You need to unclick that.
Where? Okay. Where is it? Where is it? Screen share button.
You'll be having in the bottom
View active
4
camera.
icons. Yeah, my camera and screen
yes,
button.
yes. Oh.
Yes, you need to click on that.
Okay. Not my camera. Yes, my camera. Then share.
Yes, you need to click that share button.
Okay. Reconnecting. No screen. That is 3 dots is there, and another one is camera. Then mic. After that, the screen of this.
Yes, you need to click on that screen share screen button.
Yes.
So that you are able to share your screen to us. So please click on that share button.
No screen or cameras are being shared. Oh. Copy meeting, send invitation, copy meeting information. That is, in the bottom there are 3 dots. That is audio
Yes,
option,
in the bottom,
edit your information, send an invitation, help and feedback, view active cameras.
In the bottom of you'll be having 4 icons. One is mic, another one is camera, and third one is the screen. You need to click on that screen button.
Okay. Next, look at reconnecting. Check your net.
I think he's having some technical issue. Okay, he's trying. Dr. Srinivasan?
Start now. Go to meeting. We'll start capturing everything that is displayed on your screen. Okay?
Yes.
Don't show again. Yes. Go to meeting. We'll start capturing. Yes. Start now. Okay?
Yeah. Okay.
Now my screen is there.
Your screen is not visible to us.
Not connected, huh?
You can find 4 icons. Yes, now it's there. Please share your presentation. Now we can see your screen.
Okay. Now my screen is there.
Yes, we can see your screen now. Please share your presentation.
Yes, yes. Starting the slide.
Yes, you
Are
can
you
start
visible?
your presentation now. Yeah, it's now visible.
Okay. Now,
Make it as a full screen. You'll be having one slideshow button top of it after that search,
yes,
so that it will be. I think no, your presentation is rotated.
rotated. Okay,
Yeah,
okay.
now it's
Just wait.
perfect.
Sorry, ma'am.
It's okay. Now it's perfect. Please.
On to other device. Yes. Now mathematics. Okay.
Yes.
The
Now it's
screen, the
perfect.
mathematics. Do you?
Yep.
Okay. Yes, yes. Good evening. I am Dr. M. Srinivasan from Annamalai University, India. My topic is performance analysis of multi-server retail queuing with heterogeneous server using matrix geometry method. Yes. First of all, I thanks the organizer of the international webinar on applied sciences and engineering. The mathematics is split into two forms. Generally, we say that deterministic and non-deterministic. This my audio is there, ma'am? Audio?
We can hear you. You can
Yes, we
continue.
can hear you.
Yes,
Can continue, doctor. We can hear you.
Okay, okay. Thank you. Then, what is deterministic? The deterministic solutions are determined to hold true with absolute certainty. Non-deterministic, the solution or outcome is a prediction with uncertainties that can be measured using chance or probability. We decide deterministic. What is the example for it? In India, that is sure event. That is every Sunday is a holiday. Here in Sunday is a compulsory holiday. That is sure event. Non-deterministic, that is not sure event. Here every Saturday may be holiday. That is not sure event. Mathematical definition of probability. How to mathematical definition is there? Probability. Let S be the sample space and A be the event associated with the random experiment. Let N of S and N of A be the number of elements of S and A. The probability of event A occurring, we note that formula, probability of A equal to N of A by N of S. What is N of A? N of A is the number of favorable to A, and N of S is exhaustive number of cases in S. This is the probability of the definition. For example, we take the probability of getting an even number in the tie dosing experiment, that is 0.5. How we choose? Total S equal to, that is S means the number of exhaustive, that is N of S equal to, from that S equal to 1, 2, 3, 4, 5, 6, that I say. A equal to even number 2, 4, 6. Therefore, we find that N of S equal to, and N of A equal to, we substitute that P of A equal to, the result is 0.5. Next one is the axiom, that is definition of probability. What is this? Let S a sample space and a capital A be the event associated with random experiment. The probability of the event A is defined as a real number satisfying the following axiom. We know that the axioms are 1, in between 0 and 1, 0 less than or equal to PA less than or equal to 1. And the second one is total probability equal to 1, P of S equal to 1. And the third one is if A and B are mutually exclusive, we find that probability of AB equal to probability of A plus probability of B. From that we define generating function. What is generating function? Let A0, A1, A2 be the sequence of real numbers. Using the variable S, we add the term in the form of A of S equal to A0 plus A1S plus A2S square plus A3S cube plus etc. The value is summation k equal to 0 to infinity ak s power k. This is a generative function. From that we define probability generative function. What is this probability generative function? X is a random variable that assumes non-negative integer values 0, 1, 2, 3, etc. The probability of xk, x equal to k, that is pk. What is k? K is 0, 1, 2, 3 value. From that, ak to be the probability pk, what is the k? K value is then sigma pk total probability equal to 1. The probability of pk is known as probability generating function. The probability generating function is denoted as pgf. Next one is p of 1. What is p of 1? Total probability equal to 1. The series p of s converges absolutely and uniformly in the interval in between -1 and +1 and is infinitely differentiable, then the function p of s is defined as pk. The p of s equal to, this is the formula, sigma k equal to 0 to infinity p of x equal to k s power k, that is expectation of s power k. What is expectation of s power x? That is the probability of function s of x of the random variable x. We know that the first two derivative of p of s. What is this? First derivative is b dash of s. What is b dash of s? Equal to sigma k equal to 1 to infinity kpk s power k minus 1. The second derivative p double dash of s. What is this? Sigma k equal to 1 to infinity k into k minus 1 pk s k minus 2. This is k equal to 2 to infinity. The expectation of e power x is given by expectation of x equal to sigma k equal to 1 to infinity k pk. We take another word, limit s tends to infinity p dash of s, that is p dash of 1. This is expectation of x. Suppose expectation of x square, second moment, expectation of x into x minus 1 plus expectation of x, that is p double dash of 1 plus p dash of 1. Hence we use that variance. What is variance? Variance of x equal to expectation of x square minus expectation of x whole square. This is for p double dash of 1 plus p dash of 1 minus p dash of 1 whole square. As s tends to infinity, sigma k pk diverge expectation of s equal to infinity. If x sigma k into k minus 1 pk diverges, then p double dash of 1 equal to infinity and variance of x equal to infinity. The mean and variance of x in terms of probability generative function of x, more generally, kth factorial moment of x is given by expectation of x into x minus 1 into x minus 2 etc. x minus k minus x of x minus of k minus 1, that is k plus 1 equal to k time differentiation of p of s divided by, that is with respect to s, the value of s equal to 1. This is for kth factorial moment. Now we change over to Bernoulli distribution. What is Bernoulli distribution? X be a random variable that assume only two values, 0 and 1. Probability of x equal to 1, this is p. Probability of x equal to 0, this is q. That is p plus q equal to 1. Therefore q equal to 1 minus p. Totally 0 less than p less than 1. The probability generative function of the random variable of Bernoulli distribution x is the expectation of e s power x equal to q plus sb, and the expectation of x equal to p, and variance of x equal to pq. This is Bernoulli distributions, variance and the expectation. The independent trials with only two possible outcomes are each known as Bernoulli trial. That is denoted by 1 and 0. Success is 1, failure by 0. Their probability by p and q respectively. We then Bernoulli distribution, and x is called Bernoulli random variable with parameter p. Then next move on to binomial distribution. That is x be a random variable denoting the number of success or failure in a fixed number n of Bernoulli trials, then x has binomial distribution having probability mass function. This is probability generative function of x is p of s equal to q plus sp whole power n. Here expectation of the x mean is np and the variance is x variance of, that is variance of x equal to npq. Then move on to Poisson distribution. Let x be a Poisson distribution, vary with probability mass function pk equal to probability of x equal to k e power minus lambda power k by k factorial, where k equal to 1 to 3. The probability generative function of Poisson distribution is given by p of s equal to sigma k equal to 0 to infinity pk s power k. The substitute the value, that is e power lambda into s minus 1. Here expectation of x and variance of x equal to lambda. These two are same. Therefore, we take that every problem we defined that Poisson process is used for the model of queuing theory. Next one is geometric distribution. Let x be a random variable with geometric distribution pk. Pk equal to x equal to k q power k into p, where k equal to 0, 1, 2, 3, etc. From that geometric distribution, the probability generative function is p of s equal to sigma k equal to 0 to infinity pk s power k. The result is p by 1 minus qs. Here expectation of x equal to q by p and the variance of x equal to q by p square. From that we define discrete random variable. Let x is a random variable which can be take a finite number or countably infinite of values. For example, a simple experiment like throwing a true die, that is the discrete random variable, and another one is continuous random variable. X is a random variable which can take all values in an interval, that is continuous random variable. For example, the length of time during which a vacuum tube is installed in a circuit. This is discrete and continuous. Now we move on to our topic, random process. This is the random process. What is the definition of random process? Family of random variable which are functions of time. This is the random process, stochastic process. Okay. For example, a simple experiment like throwing a true die, xn n greater than or equal to 1 is outcome of nth throw a family of random variable such that for a distinct value of n equal to 1, 2, 3, etc. and gets a distinct random variable of constitute. Next, we want to move on to the classification of random process. Discrete time, discrete state phase. Discrete time, continuous state phase. Discrete time, continuous time, discrete state phase. And the last is continuous time, discrete state phase. Then the subset, that is the term is called queuing theory. The analysis of queuing theory describes and a real world phenomena through the probability theory leads stochastic model. Queuing theory is one of the most important field in the stochastic modeling. Next is history of queuing theory. The queuing theory has its origin in 1909 when A.K. Erlang published his paper relating to the study of congestion in telephone traffic. The father of queuing theory, Danish engineer who in 1909 experimented in the fluctuating the demand in telephone traffic in Copenhagen. In 1917, he published a report addressing the delays in automatic telephone dialing equipment. At the end of the World War II, his work was extended to more general waiting line in business. What is waiting line? That is a queue. A queue is waiting line which is usually formed in front of some service facility. We see that the queue is waiting line which is usually in front of some service facility. For example, wait to eat at restaurant. Wait to line at grocery shop to check out. These are the examples of queue. And the third is wait in beauty parlor or barber shop. Then components of basic queuing process. There are queuing system considered with queue, service mechanism, and customer. The calling population come into the queue, then getting the service from server and leave the system. That whole term is called queuing system. The customer arriving for calling population, that name is called arrival process. And the queue configuration is also there. And one more is queue disciplines are also there. Then service mechanism, there is service process is also there. How to service. These all things are basic for idea about queuing system. Now, queuing system. Queuing system can be described as customer arriving for service, waiting for service if it is not immediate, and if having waited for service, leaving the system after being served. For example, all the grocery store, that is called system. All the shoppers are customers. The checkout clerks are called denoted as servers. In the toll highway is a system, queuing system. All the vehicles are customers. The toll gate is for server. In factory, there is a system. The products are customer treated as a customer, and the workers are servers. This is the form of queuing. Next one is the components of basic process, the calling population. What is the calling population? The population from which customer originate. The size can be finite or infinite. It homogeneous, only one type of customer. Heterogeneous, several different type of customers. Then is arrival process. Here we use that determines how, when, and where customers arrive to the system. The arrival pattern of customer refers the manner in which the arrival occur. It is specified the inter-arrival time between any two consecutive arrival. Therefore, we using the Poisson process. The customer may arrive singly or batches. Suppose the single arrival. This is Poisson process with rate lambda. Inter-arrival time are independent and exponentially distributed. The average inter-arrival time is 1 by lambda. That is inverse of the Poisson rate. See that this is the figure. This is the single arrival. All the interval time, the customer comes into that, but getting that single man to arrival. That is interval time of single arrival. Next one is batch arrival. Some sources transmit in packet first, may be better modeled by a batch arrival process. For example, first packets arriving according to the Poisson process. See that figure? The customers are arrived in the batch of the batch arrival. From the train or airport, the customers leave from the aeroplane. The customers come into that station, airport station. They are batch number of peoples. That is batch arrival to this. Next one is components of basic. That is the queue configuration. The queue configuration is specifies the number of queues, the single or multiple line, to a number of service session. Their effect of customer behavior. What are the behavior? The behaviors are customer behaviors are balking, reneging, and jacking. Now, what is balking? Balking customer. The arriving customer saw the queue is too long. See that the queue is too long. If the customer decide not to enter the queue upon arrival is called balking. Customer see the queue is so empty, then the customer decide to not enter the queue. That type of customer is called balking customer. And another one is reneging customer. Renege. The customer may enter the queue, but after that he may decide to leave the queue. Impatient is renege. Customer first enter the queue. After that he decide to leaving due to impatience. That is renege. See that? Just wait fourth or fifth people so many time. Then we want to go back. That is renege, impatient customer. See that? This is the queuing system. Renege. Next one is jacking. What is a jacking customer? If there are two or more parallel channel, customers are switched from one queue to another. That type of queuing customer is called jacking. See that? Waiting line. There are server A, server B. Server A 3 customers are there. Server B 4 customers are. Then server B customer went into server A, but the server A is closed. Then they will move on to another server. That type of customer switching over to the queue, that is called jacking. Next one is periodic type. Non-primitive. High periodic customer must wait for a low periodic customer found under transmission upon arrival. That is non-periodic. Suppose primitive is high periodic customer does not have to wait. Straight away go to service. That is periodic customer. Next one is periodic customer. There are 3 types: class 1, class 2, class 3. In the red, that is high periodic customer, get the service, transmission line, and leave out the system. And another one is green, arrival term, that is periodic customer. They enter into the server, get the service, leave out the system. Last third is black, that is arrival low problem periodic customer. They wait for the queue and getting the service and leave the system. There are 3 type of classes we divide. And one more is feedbacking system. What is feedback? After service completion, a customer may, under some decision rule, independent of remaining stochastic behavior of the system, return to the waiting line to receive another service. See that? Feedback loop. Here, Q get the service yes and went to the N. The customer returned to the queue, then getting the another some questions are clarified in the server. That then we take out. That type of customer is called feedbacking system. Then analysis, performance analysis of queuing model. The mathematical formulation is solution and calculation of some statistical characteristic. That is performance analysis. The mathematical formulation is obtained by assuming some probability distribution on arrival pattern, retrial period, service pattern, etc. The solution of the model are obtained in time independent, in time dependent domains called steady state solution or transient solution. The statistical characteristics are performance analysis. That is mean number of customers in the system, mean number of customers in the orbit, mean waiting time. These are the performance analysis of the characteristic. Then retrial queue. Our aim is retrial queue. In the queuing system, if customers arrive for service and find all servers are accessible to them or busy, leave the service area temporarily, stay in orbit and repeat their demand after some random period of time. Here the server is ideal question mark. If yes, then getting the service time, that is called mu departure. Suppose the server ideal is no, the server is busy, then the customer goes to some place, whatever it is, that place is called orbit. After some time from the orbit, the customer enter into system, that is retrial. That queue is called retrial queue. Then service pattern. Up to that we study about arrival pattern. Next is service pattern. What is service pattern? The service pattern of server refers the manner in which service is rendered. It's specified by the time taken to complete a service. Service may also singly or batches. The service process may depend on the number of customers waiting for service. Two queue configuration. We see that single queue, here multiple queue. The right side is server, 4 servers are, that is, but the queue is only single. Or multiple queue, the servers are 4 servers, but the in between the server there are 4 lines are there. There is multiple queue. Queue discipline. This is one character. The customer queue, the common queue discipline is first come first server. It is called first in first out. The appreciation is FCFS or F5 F0. And another one is last come first service. That is warehouse and godown. In the godown, the material is the last come material should be delivered in the first. Therefore, last come first. That is called warehouse godown. The example of this. Then service in random is also a queue. Now our topic is single server queuing system. See that this is arrival of the customer, enter into the transmitter line, is getting the service, is called single server queuing system. Suppose multiple server queuing system, head of the line service customer wait in the queue and then server becomes free, the first customer goes into the service. That type of queuing system is called multiple servers. Another one is waiting time. The waiting time in queue refers the time spent by the customer in waiting before service. See that the waiting line, processing order, the waiting line and service combined together system. The arrivals are coming and get the service, exit the customer from the system. The waiting time in the system is waiting time before service plus service time. It's called waiting time in the system. See that. Next one is a busy period starts with an arrival at an empty service. The facilities and ends with the number of customers in the system drops to 0 for the first time, and then an ideal period starts with the end with the commencement of the next busy period. That interval is called busy period. See that this is busy period. Next one is vacation time. After servicing a certain number of customers ruled by specific service discipline, the server may become unavailable for a period of time called vacation time. Next one is the vacation setup. See that? Other one is working vacation. The vacation time, see, worked during the vacation time. If there are customers waiting for service, the server may serve as the customer with lower rate of service rather than completely stopping the service. Next is vacation interruption. What is the meaning? The server stops the vacation if the number of waiting customers achieving a certain value during the vacation. Server breakdown. A queuing system might suddenly break down and hence the server will not be able to continue providing the service unless the system is repaired. That is, WhatsApp is server down. This is called breakdown. Next one is heterogeneous servers. Our topic is queuing model with the heterogeneous server. What is heterogeneous server? Service time distributions may be different for different server. That is, each and every server getting our own service mechanism. That is called different servers time rate. Another one is catastrophic queuing system. That is, catastrophe means all the customer in the system is destroyed immediately. Next one is restoration time. The system takes its own time to be ready to accept new customer. This time is called restoration time. Next one is the system capacity. The number of service channel, single or parallel. See that? Parallel, single channel. Number of service stages, single stage of, it may be several stages. Feedback also there. Next, our notation is Kendall notation. The model is A, B, X, Y, Z. What is A? A denote for interval time distribution. B denote the service time distribution. And X is the number of parallel channel. And Y the system capacity. And Z denote the queue discipline. This is the queuing model, multi-server queuing model. And what is A? A is a Poisson process. That M is a Poisson process or exponential distribution. Usually note that. And EK Erlang K distribution. And G general distribution. D deterministic interval. This is an example for how to find the result. Establishment the probability of X equal to e power minus lambda into lambda power X factorial. This is how to find. This is a formula. The question is, if the average arrival rate per hour is 2 people, that is lambda equal to 2, what is the probability of 3 arrivals per hour? This is the question. The solution is how to find. Lambda equal to 2, formula know that we substitute, we get 18% of this result. Then exponential distribution, queue length, probability of T, probability that service time will be greater than the T, probability of T equal to e power minus mu t, that is exponential of u minus t. Some queuing model, MM1 queuing model, that is single server with finite capacity. M is Poisson arrival distribution. Another one red, that is negative exponential service time distribution. And the one blue, that is single channel single server model. This is MM1 queuing model. Next one is MMS multi server with infinite, that is M is all same, and another one is same, but here S is there, that is multiple channel. And another type is MM1K single server with finite capacity. The same M is the same Poisson arrival distribution, and another M is same but single server, and another K is called system capacity is K. Other type is MG1 single server queuing system with the exponential interval time distribution and arbitrary service time distribution. The same as M, but G is general distribution. One is single server. From that we find out little formula. L equal to lambda W. Assume that lambda n is the
Hello, Dr. Srinivasan. We are unable to hear your voice and presentation. Am I audible to you? Dr. Srinivasan, can you hear me?
If you mean Dr. Mikhail Halaris, yes, I hear you.
Yes, doctor, but he's having some network issue, I think, so we'll contact him just a moment. Dr. Srinivasan, are you there? Just a moment. Dr. Srinivasan, can you hear me?
Yes.
I think he is having some network issue. We have contacted him also. But hello, Dr. Srinivasan, we can't hear your presentation. Hello, can you hear me? Hello. Hello, Dr. Srinivasan. Dr. Srinivasan will be joining in within few minutes. Is having some network issue. Thank you for your patience. I think Dr. Srinivasan has joined in the webinar.
Okay.
Doctor, can you hear me now?
Yes, yes. Just
Yes,
wait.
please continue.
Yes,
Please
yes,
continue.
yes. Just one. Okay. Okay, okay. Hear me. Heavy rain, man. Okay, sorry. Yes. Our conclusion is we want to find out from that probabilities. From the probabilities, we decide that performance analysis of that particular term. Not screen, huh? Okay. The last is references. Sorry for the interruption.
Yes, doctor, please
To
continue.
share your screen. Yes, yes, yes. Yes, I only 2 more slides. That is only for ending this. That is conclusion, and another is reference. Okay.
Okay, please
Any question?
continue.
Not sharing.
Doctor, is your presentation is completed?
Yes. Yes. Yes.
Okay.
Yes. Yes.
Okay, thank you for your presentation. Is anyone having any questions? I think there are no questions. Thank you once again for your presence and presentation, Dr. Srinivasan. Let's move to our next presentation by Dr. Michael Charles from International Helsinki University, Greece. Doctor, are you ready with your presentation?
No, if is it is possible to share the
Yes,
screen?
I'm going to make you as a presenter now. Please share your screen.
Is it visible my screen?
Yes.
Okay, I would like to thank the organizing committee to invite me to present theories and trends in porosimetry. First of all, I would like to introduce my laboratory. IFESTUS is an advanced research laboratory within School of Science of International Hellenic University, worth more than 15 million and comprising three main sections: material science, that covers the area of porous materials from synthesis to characterization, and from nanotechnology to oil and gas reservoir engineering, such as catalysis, membrane technology, flow in porous media, and some examples. Electrical engineering that specializes on remote electrical measurements, and mechanical engineering that covers metrology, robotics, and renewable energy systems. IFESTUS Lab aims to serve as a center of excellence, both academia and industry, locally and internationally, to this direction towards a successful development of innovation ecosystem in our region with a possible contribution to the global problem. Porosity is the pore space in a material. Internal surface of material comprises the pores and cracks that are deeper than they are wide. Porosity refers also as a void fraction and is measure of holes in the material. There are many techniques to characterize the internal structure of powders or porous solids. The most two reoffered techniques for the porous characterizations are the gas sorption and the mercury porosimetry. According to the IUPAC, porous are classified in three categories: microporous, that means pore diameter is less than 2 nanometer; mesoporous, the pore diameter is between 2 nanometer to 50 nanometer; and macroporous, the pore diameter is greater than 50 nanometer. The nitrogen absorption and the mercury porosimetry are complementary techniques. Usually the nitrogen gas absorption used for the characterization of micro and mesoporous materials, and the mercury porosimetry used for the macroporous characterization, such as we can see that in figure in this transparency. In the next slides, I will describe the basic theories for micro, meso, and macroporous characterization, and I provide information which can be extracted for the mentioned techniques. The most common informations are pore size, surface area, and pore size distribution. The physical and chemical processes by which one substance becomes attached to another or released from it called sorption. The sorption divided into two processes, absorption and desorption. In absorption procedure, a film of the absorbed bait created on the surface of the absorbent. The desorption is the opposite process of sorption. In this, we can see here a simple schematic of the sorption procedure, and several methods are developed based on the gas sorption for the porous characterization. The most used of them are BET, Langmuir, VT, DRDA, and so many, etc., which will be described in the following slides. In this figure, we can see the different porous characterization methods according to different relative pressures. The bed theory is the most widely used method in surface science for the calculation of surface areas of solids by physical adsorption of gas molecules such as nitrogen, helium, argon, krypton. The bed theory was published in the Journal of American Chemical Society in 1938 by Berner, Emmett, and Teller. Two different expressions of bed methods can be found: the simple point method and the multi-point method. For the calculation of the surface area of solid materials, the bed equation is this one, where P is the equilibrium pressure of absorbates in Pascal, P0 is the saturation pressure of absorbate in Pascal, and U is the absorbed gas quantity in mole. The UM is the monolayer absorbed gas quantity, and C is the bed constant. The bed constant is related to the energy of absorption for the first layer, and if energy L is the heat of absorption for the first layer, and the E2L is equal within the heat of liquefaction, R is the mole gas constant in G in joule mole -1 Kelvin -1, and T is the temperature in Kelvin degrees. The bed constant is described in this equation. The bed plot is maintained in the range between 0.0 pressure to pressure 0 between 0.35 in the linear plot. We saw the typical bed plot. In the bed plot, and from the slope S and intercept I, it is possible to calculate the weight of a monolayer, the UM, and the bed constant with the use of this equation. We saw the equation in this slide. The total surface area of the sum calculated from this relation, and at the end, if the total surface S is divided by some weight W, the specific surface area is given by this equation. Here is the what is its quantity and the units of its quantity. The single point method is used for a fast calculation of the specific surface area compared with the multi-point bend method, and it is used for routine measurements if the values of C is sufficiently large to ignore the value of I. This is the equation. This equation becomes in this form, and after the combination with the ideal gas equation, we will take this equation. For the calculation of the previous parameters, need only to measure the amount of nitrogen absorbed and only one relative pressure, usually near to 0.3. The Langmuir equation is a simplified equation of the bed equation and can be used only in type N absorption isotherms. If W is the weight of absorbate and at P to P0, and WM is the weight of monolayer, and C is the constant associated with the energy of absorption, is not the bed constant, this set. The equation is given by that form. The Langmuir plot is a plot of P to P0 to W versus P to P midem, and from the slope of Langmuir plot is possible the calculation of the weight of monolayer the WM. From the Langmuir equation can calculate the surface area with the use of this equation, the previous equations, and the limitation of the Langmuir method is not applicable to characterize micro and mesoporous materials. Another method for the determination of the surface area is the Harkins-Jura method, HK. The HK method is an empirical method and does not require the volume of gas, which is required from a monomolecular layer. The HK method involves the gas pressure and the volume of adsorbed gas, which measured during the experiments. This is the relation and what means each quantity. The Harkins-Jura method plot is a plot which, solving the previous equation as per S, can calculate the specific surface area, and this method can be used for the S in a range of 0.01 between 0.13 of pressures to pressure 0. It's mean the gas pressure to the saturation vapor pressure. If this result is between 0.01 to 0.13. Now we are talking about micropore characterization. Several similar methods used for the micropore characterization. The most common are the V-10 method, the alpha S, the MP, the DR, the DA, the HK, and the SF. One of the most popular methods to calculate the thickness of a layer of adsorbate on the porous walls at a certain relative pressure is with the use of V-T plot. The V-T plot is plot of the volume of the gas adsorbed versus the statistical thickness T of an adsorbated film. Three different but similar equations can be used for the calculation of the statistical thickness in the V-T method. The three equations are the De Boer, carbon black, Hasley. All the previous equations are used only for nitrogen adsorption at the temperature of 77 Kelvin. If the gas and temperature are different constant numbers, using the equations must be changed. A typical T curve shown in this diagram. From the slope of this T plot, it is easy to calculate the total surface area with the use of this equation, where S is the slope of T plot, and when the intercept of the plot multiplied by 0.001547 give the micropore volume. Another method is the alpha S method, like the T plot, but compares the experimental data on porous solids with adsorption on selected standard materials. It allows to determine not only the content of microporous, but also mesoporous, as well as macropore external material. I is most often used for nitrogen data, but it can be used also for other adsorbates. However, every type of adsorbate and determination of a fixed relative pressure is required. The fixed relative pressure is 0.4 for nitrogen. In 1968, Michael Brunner and Bodor proposed an extension to the De Boer's T method for micropore analysis. The advantage of this method is that the calculation of the T is dependently of the solid. The value of the T comes from the equation, and then the values of T used of construction of volume versus T plot using linear slope constructed for T values intervals from the origin to 4 angstrom to 4 to 45 angstrom, etc. And when the slope to decrease, then we calculate the calculation. I'll stop also. This is what I described before. And pore volumes can be calculated using this relation, where Sn is the surface area calculated from slope 1, S0 is the surface area calculated from slope t, tau 1 is the thickness at beginning of interval used for slope 2, tau 2 is the thickness and the interval used for the slope 2. Another method, the DR method, the Dubbin-Raduskevich, is used to express the adsorption isotherms in micropores. For the use of DR equation is required a saturation pressure which is not defined for supercritical conditions. According to Dubin and Raduskevich, a Gaussian function can be used to express the fraction of the adsorption volume V occupied by liquid absorption at various adsorption potential. This is the equation, and a plot of isotherm data as a log of the absorption volume versus log for pressures and saturation pressure into square is used for the calculation of micropore volume and for the characteristic energy of adsorption. The DR method is used at P2, P0 are less than 0.01. In 1960, Dubin and Astakov proposed another equation for the calculation of micropores volume, and especially when the previous DR method fails to linearize the adsorption data. The DR equation used for materials with heterogeneous distribution on strongly activated carbons. This is the equation describe all this theory, and a plot of logarithm of V versus gives a line with a slope and intercept of ln to the limiting micropore volume. The DR method is used when the pressures and the saturation pressure is less than 0.01. Another method is the HK method. In 1983, Horvath and Coalesce developed a method for the finding of the pore size distribution in microporous carbon using nitrogen adsorption measurements at 77 Kelvin. This method is independent of the assumption of capillary condensation phenomenon. The HK method is a semi-empirical method and describes the adsorption potential function within slit like microporous as a function of the effective pore width, and the HK equation is that one, a large equation with many quantities. What mean AS and AA? This is the what's mean its parameter. Another method is a site of Foley as an alternative method of Horvath and Coalesce HK method is the site of Foley method, which proposed by the site on Foley in 1991. This method is independent of assumption of capillary condensation phenomenon, as HK method is better for solids that usually have a cylindrical pore geometry like zeolites. In the decade of 90s, several articles published in the field of fluid behavior in non-homogeneous systems. In 90s, the density functional theory applied as a practical method for reducing isotherm data. Finally, in 2000s, different dimensional functional model applied to a variety of absorbate systems and pore shapes. The molecular simulations with Monte Carlo, the DFT method, and the molecular dynamics provides more accurate results in the pore size analysis than the previous described methods, BJH, HK, and SF. Usually, the combination of non-local DFT and of grand canonical Monte Carlo simulation is used to describe the local fluid structure near curved solid walls, and the relation between isotherms determined by microscopic approach and experimental isotherm on a porous solid can interpret in terms of a generalized adsorption isotherm equation. It's given, this is equation, and of course many different methods have been developed and used in nowadays. NLDFT, GCMC. In 1983, Evnir and Feirer introduced first time the fractal analysis from nitrogen isotherms. The rotates of the surface structure of different solids can be determined by the fractal dimension D. Usually, a real surface varies between 2 and 3. The determination of D can be found using different methods, but two of them are the most popular. This is the Frenkel-Wesley-He method, and the other one is the Neyman-Kislev method. In the first one, in the FHH method, the proposed model for multilayer adsorption is a method which determines surface fractal dimension from a single adsorption isotherm. The surface fractal dimension from this model given by this equation, where n is the number of absorbed moles of nitrogen at given relative pressure, and Nm is the number of adsorbed moles in monolayers, and the values of Nm and N can be obtained from the BET model equation. The surface fractal dimension they can be calculated from the slope of a plot of ln N to N versus ln P0 to P. About the Neyman-Kislev method is combination of Neyman-Kislev equations, fractal and thermodynamic arguments. The capillary condension fractals follow this equation. SR is expressed in terms of the absorbed vapor interfacial area. SLG, that in turn is given by the Kisilev equation. This is the Kisilev equation, where rho being the universal gas constant, tau the absorption temperature, gamma the LJ interfacial surface tension, Vm the adsorbate molar volume, P to P0 the relative pressure, where P0 is the saturation pressure, and finally N and N max are the amounts of gas adsorbed at P to P0 and at saturation respectively. And now we are going to mesoporous characterization. We start to describe the Barrett-Joyner-Halenda method, BGH. The pore size distribution, PST, can be calculated with the use of this method. The assumption from the BJH method uses all pores have cylindrical geometry and all pores are filled with liquid when the relative pressure is close to 1. This method is based on the reducing of thickness of absorbed layer for a pore in the case of relative pressure is lower than 1. At the same time, the radius of the inner capillary is reduced also. If the procedure continues and the relative pressures become lower than the volume of liquid dissolves, includes the condensate from the next larger size pores and the second thinning of the physical adsorbed layer. all these mechanisms expressed from this equation. What minutes parameter is here, and I would like to mention that factor AC can be calculated from the area of each pore. The area of each pore is constant and expressed by this equation. Another method is Delimore and Hill method. Is very similar to BGH method for the PSD. The assumptions are all pores have cylindrical geometry and are empty of contested previous desorption steps. This method, DH, is simpler than the previous one, BGH, because the fact is calculated by this equation, where sum of LP is the length of all pores emptied of condensated in previous desorption steps. Sum of AP is the area of all pores emptied of condensated in previous desorption steps, and the lengths can be calculating from this equation. One method is the Favas-Mitropoulos-Stephanopoulos method. Professor Mitropoulos is co-authoring this presentation. In 2011, Favas, Mitropoulos, and Stephanopoulos proposed a simple equation for accurate mesopore size calculation. The FMS method is an empirical method which satisfies the thermodynamic requirements of capillary vaporization and allows a calculation of the mean pore size. The simplest form for the calculation of pore radius of mesoporous material is given by this equation. Rp is the pore radius, Rk is the Kelvin radius, T is the thickness of the absorbed film, and delta is the correction term for the interaction between adsorbate and substrate. Based on experimental data, they propose a reduced version of this equation, which overtakes many of the standard methods' limitations without loss of simplicity. And we will finish with the macroporous characterization. The most appropriate method for macroporous characterization means pores within width more than 50 nanometers is the mercury porosimetry. Mercury porosimetry gives information such as surface area, pore size distribution, pore size length and particle size distribution porosity, tortuosity, permeability, fractal dimension, and etc. This characterization technique is based on the external pressure which need to force the mercury into a pore against the reverse force of the mercury surface tension. Mercury porosimetry based to this equation is a Washburn equation, where P is the pressure, R is the pore radius, gamma is the surface tension, theta is the constant angle, and represent the relation between pore radiation and pressure. The surface is calculated from this curve, which is an intrusion curve and is plot for penetration curve versus pressure, like this figure, and the equation of calculation of the surface area is given by this equation, and the pore diameter calculated from this equation, where the mean dAm is the mean pore diameter, Vt is the total mercury volume, and S is the surface area. The volume pore size distribution, dVd, is defined as the pore volume per unit interval of pore diameter d, and given by this equation. This is my presentation. I include all the techniques about the porosimetry. I describe all the basic theories for micro, meso, and macro porous characterization, and I provide all the necessary information which can be extracted for the mentioned techniques. Thank you very much for your attention.
Thank you, Dr. Mikkel. Is anyone having any questions? I think there are no questions. Thank you once again for your presence and presentation.
Thank you very much.
Thank you. Our next presentation is by Dr. Selvian, but due to some network issue and technical issue, he was unable to attend today's webinar. So he'll be joining with us by tomorrow. And Dr. Soida also having same issue with the network. So she'll be joining with us by tomorrow. By this, we came to end on day one webinar. I would like to thank all the attendees and participants of today's webinar. Hope you enjoyed the webinar and gained the knowledge from the sessions. And I request you to attend tomorrow's session too. If you have any queries, you can mail to the concerned program manager. Thank you once again for your presence and presentation. Thank you.